Dr. Asif Hakim from ISER Mohali. Dr. Asif Hakim, please go ahead and present your work.
Yeah. So, hello and good evening, good morning, everyone. I am Hasib Hakim, and I am a postdoctoral fellow at the Department of Earth and Environmental Sciences at ISER Mohali. So, first of all, I would like to thank all the organizers for giving me this wonderful opportunity to participate and present in the greenhouse gas workshop. And title of my today's talk is Paddy Fire Exhalations of Carbon Dioxide and Methane, the results of long-term greenhouse gas measurements from ISER Mohali Chemistry Facility. So as I said, I'm here to talk about the carbon dioxide and methane emissions and focus on paddy stubble burning as a source. So let me introduce you to the region and show you how the meteorological conditions changes over the course of an year. So all of the primary measurements presented today were collected at the ISER Mohali Atmospheric Chemistry Facility in Punjab, which is a regionally representative site in the northwestern Indo-Gangetic Plain. So the site, which is shown as the black dot in the map, is located close to the forested slope of foothills of Himalayan mountain range. And on northeast of the site is urban agglomeration of Chandigarh and Panchkula. And as you can see, more than 80% of the land use is agricultural. So the region has an intensive rice wheat cropping pattern. And also this is a strategic location because we sample the agricultural region most of the year, but during monsoon season, we receive air from southeast that has traveled over the IGP as well. Now here, the figure shows the monthly average trend of relative humidity, ambient temperature, and solar radiation at the measurement site. As you can see, the meteorological conditions vary significantly throughout the season, making our site an ideal location to examine the extremes of atmospheric chemistry. The wintertime months of December and January are characterized by dense fog, as can be inferred from the high relative humidity and low solar radiation. And summer is characterized by high daytime temperatures, intense solar radiation, and dry condition. And the start of monsoon season, we determine on the basis of the first rain event after the prevailing wind direction switches from predominantly northwesterly southeasterly flow. And in the monsoon season, there has high relative humidity, and we experience heavy rainfall, thunderstorms, and diffused solar radiation due to cloud cover. And the post-monsoon season marks the transition period between monsoon and winter season. So here I will talk about the paddy stubble burning. So the paddy cultivation usually begins in late June. The crop attains maturity by late September, October months. And the harvest of the crop takes place in October, November using combine harvesters that leaves behind a large quanta of paddy stubble as the unutilized residue. The most frequent and cheapest disposal practice here is to set fire to the paddy residue, which results in large-scale emissions of multitude of gas as well as aerosol species, causing massive air pollution episodes across IGP. And it has got so much of attention. Since the air pollution is so severe, most of the time we do not think about how much greenhouse gas is being emitted from such activities or what is the source contribution of carbon dioxide and methane. And actually, paddy stubble burning could potentially be a significant source of greenhouse gas, especially for this time of the year. So we will look more into that. So the measurements of greenhouse gases were made using a cavity ring down analyzer, and basically, the CRDS is a sensitive spectroscopic technique that make use of an optical cavity to measure absorptions on the order of parts per million and beyond. And in CRDS, what happens is that a light from a semiconductor diode is passed through a high precision wavelength monitor to a finest optical cavity defined by 3 highly reflective mirror system, as you can see. This light then circulates in the cavity multiple times, resulting in an effective path length of so large, effectively 20 kilometers or more. This high precision of CRDS comes from this very long path length, providing low detection levels for the sample species. And then a photodetector senses the small amount of light transmitted through one of these mirrors to produce a signal that is directly proportional to the intensity of light inside the cavity. And when this signal from the detector reaches a threshold value, the laser is switched off through a feedback mechanism. Now that there is no input, the energy decays through loss mechanisms exponentially in time. This energy decay is measured as a function of time on the photodetector and is known as ring down time. And when the sample species are present in the cavity, a relatively shorter ring down time is obtained due to the additional energy consumption by the different rotational, vibrational modes of this gas species present. And the ring down time of cavity with and without the absorption due to target gas species is calculated and compared continuously to obtain the concentration. Now, to ensure the reliability of the instrument and the data quality, we do a multi-point calibration at least once in 6 weeks, consisting of a 0 and 4 upscale points. A calibration gas standard containing a mixture of carbon dioxide and methane traceable to NIST standard is used. And as you can see, an excellent linearity of CRDS from one of the calibration experiments is shown here for both carbon dioxide and methane. We can see that the instrument could be successfully used for ambient air measurements because it appears in the calibration range, and the uncertainty of instrument was also derived from the calibration experiments by considering systematic errors and propagating them. And the overall uncertainty of the measurements that I'm going to show are in this presentation as always below 4%. Now, this figure indicates the time series plots of monthly average mixing ratios of carbon dioxide and methane for the year 2015. First of all, as you can see, there is a distinct variability in the seasonal cycle of methane and carbon dioxide. However, it is interesting to see that the crop cycle influence is perceptible in the case of both the species. So if we go by season to season, as the season changes from winter to summer, we see that a decline in the mixing ratios of both the greenhouse gases was observed in late February, which is expected due to the growing dilution effect by the boundary layer during summer. And we see a sharp increase in the CO2 mixing ratios throughout the summer. The maximum value of CO2 is observed in May, mainly due to the contribution from wheat residue burning during the time. But unlike CO2, there is an active sink for methane in summer, which is its oxidation with hydroxyl radical to form CO2. Therefore, we see a sharp decrease in the case of methane mixing ratios from February until May. In May, the decreasing trend of methane is heavily compensated by the contribution from wheat residue burning emissions. Now, if you move to monsoon, since May, the concentration, CO2 concentration starts decreasing as we move to the start of monsoon in June. This decrease in CO2 concentration is further continued throughout the months of July and August, which is an active summer monsoon period. The low concentration of CO2 during this July, August, September is found to be coinciding with the high monsoon seasonal values of net primary productivity as well. It is also known that vegetation growth absorbs CO2 from the air, causing the carbon sink. And but in the case of methane, the monthly value of mixing ratios was observed to be lowest during the start of monsoon season, followed by a sudden jump during the month of August and September, when majority of the paddy in South Asia is grown. So this increase in mixing ratios in methane is mostly because of the activation of methane emission due to enhanced methanogenesis activity facilitated by the rice paddy fields. And the measured ambient mixing ratios for both CO2 and CH4 was found to be highest during the month of October and November period due to paddy residue burning. So it is very well captured here. So if you zoom a little into the data and look at the daily average mixing ratios in the form of a calendar plot, we can see, as you can see, the number of days with the maximum mixing ratios was seen during the months of October and November. So this influence of paddy residue burning has shown up in monthly average as well as daily average values as well. The same is the case for methane as well. The months of October, November, December, as you can see, the highest values, daily average values are observed during these months. So therefore, my next objective was to assess the enhancement in ambient mixing ratios of greenhouse gases during post-paddy harvest seasons in contrast to the pre-harvest period. So the time periods for pre and post harvest seasons were determined primarily based on 3 criteria: the remotely sensed the regional fire activity data, and the trend in ambient level of chemical tracer compounds for biomass burning, and the consistency of meteorological conditions during both the period. So here the light yellow shaded portion corresponds to pre-harvest, and dark yellow shaded region corresponds to post-harvest period. So the total number of open fires detected during the post-harvest paddy season were close to 2,000. but whereas the number of fires detected during the pre-harvest season was below 20. And on the right-hand side, we have seen we can see the time series of daily average mixing ratios of acetonitrile, a specific chemical marker for biomass burning, and CO, a tracer for inefficient combustion. So here the solid line represent the daily mean, while the shaded colored region represent the daily ambient variability as the 25th and 75th percentile. So it is evident from the time series that the average mixing ratios were generally higher in post-paddy harvest season relative to the pre-harvest season. So in particular, the mixing ratios of elevated mixing ratios of acetonitrile, as I said, a marker compound for the biomass activity during the post-harvest is indicative of the enhanced biomass burning activity, and it is consistent with the residue fires being active. So even though a clear increase is seen in the emission of the tracer compound, to attribute how much of the increment is due to fire activity, one needs to compensate for the ventilation coefficient as well. However, we have seen a similar condition during both pre and post-harvest periods. Hence, the change in the ambient mixing ratios in the post-harvest period, it could be attributed to the change in the emission activity and not because of the change in meteorological conditions. Now, if you look at the greenhouse gases, we see a similar trend to that of the biomass burning tracer compounds. The daily average concentration of both CO2 and the methane were higher in the post-harvest period, and that too by a factor of 1.2 to 1.3 times respectively. So here I examine the average dial concentration profiles of greenhouse gases to ascertain whether a dial time dependence exists for the paddy residue burning activity. So first of all, let us look at the case of tracer compounds first. The horizontal axis here represents the start time of the corresponding hourly bin. The line with the markers that connects the average hourly concentrations, and the median is presented by a cross, while the width of the box encompasses the interquartile range, and the whisker showing the 10th and 90th percentile. So in the evening hours, the mixing ratios of both acetonitrile and CO during post-harvest period was observed to be almost 2 times as that of the pre-harvest period. So this is also consistent with our field surveys and information shared by rural people that the paddy residue is generally set on fire in the evening hours when the meteorological conditions are calm, and this is to minimize the risk of fire becoming uncontrollable, and also it is easier to avoid check by law enforcement as it is legally forbidden to burn paddy residue right now. And the figure shows the dial profiles of the carbon dioxide and methane during pre and post harvest period. So the bimodal, the period during both pre and post harvest season, the bimodal profile here is driven by the dilution effect due to boundary layer dynamics. However, as I said, the presence of the secondary peak in the evening hours during post harvest period in correlation to the tracer compounds point to a primary emission source of greenhouse gas from the paddy residue. So since we have identified the significance of paddy stubble burning as a source of greenhouse gases, I also wanted to quantify how much of these emissions are coming from this particular source. So we began this work by work with the collection of all air samples of paddy stubble fires from the agricultural field in Mohali. So we at 13 samples were collected in flaming and smoldering stages separately from 8 paddy fires in villages of Raipur, Khurd and Kurari. And apart from the visual inspection, the fires were distinguished as flaming or smoldering based upon the combustion efficiency value. And then the samples were analyzed with our instrument PTRMS, TDGCFID, and CO analyzer and CRDS to obtain emission factors for 77 VOCs, CO, CH4, and CO2. And the emission factors were calculated using the carbon mass balance method. And now that we have the emission factors for the paddy residue burning activity, next objective was to quantify the emissions. For that, we had to develop an emission inventory. So the emission inventories are fundamental inputs to chemical transport models. It provides information about the quantity of a pollutant emitted from a specific source over a given geographical area and time period. So an emission inventory is compiled using 2 main parameters, emission factors and activity data. So the emission factor basically tells us the amount of pollutant emission per kilogram of biomass burned, while the activity data holds information on the total amount of biomass burned. So both these factors are highly regional specific. The emission factors, for example, depend upon the type and composition of biomass burned, such as rice residue or wheat residue, along with the regional burning practices and environmental conditions. So activity data is also dependent on regional burning practices such as short durational, partial or smoldering fires. So here in South Asia, it is very different from the large-scale crop residue burning in American and African continents that we see. However, previous to this, no such regionally accurate emission inventory exists for paddy stubble burning in North India. So here, there are top-down and bottom-up emission for top-down emission inventory such as GFAT, GFAS, etc. available, but there are uncertainties associated with such satellite-based methods. So we are considering a hybrid approach of a combination of bottom-up and top-down methodologies in our study. So this has been already published by one of my colleagues, Ashish Kumar Sharma. So the method I will briefly explain here. So here you can see the next step was the development of the hybrid emission inventory, as I said. So we started with the bottom-up calculations of the emissions by using the measured emission factors and district clockwise production statistics acquired from the Government of India. And these were then coupled to additional factors that account for the region, rice cultivators and burning practices. So once we had calculated the district-wide emissions, the next step was to calculate the top-down distribution. And for this, satellite detected fire acquired data by VIRUS was available from FIRM's database. And the fire radiative power is calculated from the radiative energy detected by the satellite in each fire, which is proportional to the amount of biomass burned in the fire. And this FRP when then gridded over 1 kilometer into 1 kilometer using GA software. And finally, a factor was calculated that accounts for the fraction of residue burned in each grid in a particular district. And finally, a hybrid emission inventory was prepared by combining both the bottom-up emission calculations and top-down distribution factors. Now, the emission inventory was the main focus of the emission inventory was VOCs, but with respect to this study, I am showing here the greenhouse gas mapping. So here the figure shows the district-wide map of Punjab and Haryana and annual gridded emissions of carbon dioxide and methane due to paddy residue burning over the region. So approximately 18 teragram of paddy residue was burnt in the fields of Punjab and Haryana in 2017, of which 90% of is burned in Punjab, and 20 teragram of CO2 and over 60 gigagram of methane was calculated to be emitted due to this burning activity. The spatial distribution of the emissions showed that the emissions are more over the Malwa region, which comprises of the central and southern states of Punjab like Patiala, Sangrur, Ludhiana, Moga, and the northern districts of Haryana like Karnal, Kurukshetra, and Fatehabad. So these regions are also known to follow an intense right wheat cropping system along with the mechanized harvesting that leads to more burning. So in addition to this, as I said, toxic and carcinogenic VOCs like benzene, isocyanuric acid, as well as PM 2.5 and BC were emitted in high quantities, which poses several health risks. Now, so here I show the inter-annual variability of paddy stubble burning emissions, including for the decade spanning from 2008 to 17. So from 2008 to 2014, the emission did not seem to have any trend, significant trend considering the uncertainties. But after 2014 until 2007, the emissions appear to have increased by almost 5% per year. This interannual variability in our analysis is completely driven by the variability in quanta of paddy straw burnt, which itself was dependent upon the crop production, yields, and sowing patterns. And also recently, the technological improvements and agricultural policies favorable for higher yields likely to also contribute to the increased production after 2014. And also after 2017, which is not shown here, the adaptation of new technologies like happy seeder machines, which sows wheat throughout the paddy stubble in many districts around Ludhiana, has reduced burning, but we need to further see how it affects the internal variability further. So then finally, I wanted to compare our new hybrid emission inventory with the other global emission inventories. And on comparison, it was found that the GFAT and GFAS underestimated the greenhouse gas emissions by up to 9 times. And our estimates were closest to FIN emission inventory in magnitude, but were still higher by a factor of approximately 2 to 3 times for both methane and carbon dioxide. And the emission inventories like GFED and GFAS and FIN, as I said, follow a top-down methodology. So the major reason for underestimation by these inventories include uncertainties in detection of the activity by satellites due to limited overpass time and poor detection of because of haze and clouds, and use of emission factors and globally generalized parameter factors that are not region specific. And so these results also reveal that the emission from the party-stable burning are up to 25 times more than the traffic and garbage burning emissions during the same months of October and November. So indicating the significance of party-stable burning as a source of greenhouse gas in compared to other sectors as well. So my future plan is to combine the in situ measurement data with the data derived from satellite observations to see if it captures the enhancement due to crop positive burning over the intergalactic plane. Currently, I'm working on quantifying the enhancement in greenhouse flux due to party-stable burning over the northwest intergalactic plane. And we have been performing online measurements of greenhouse gases since October 2014. So anyone who would like to collaborate can email us on the following IDs. This is the instrumentation or the suite of instruments that we have in our lab. Anyone who is interested can also see the publications, including the road transport and garbage emission inventories I have talked about. And thank you.
Thank you, Dr. Sivakim. We have a few questions for you.
Yeah.
So I will start with one by one, and you can answer those questions. Yeah. First, I will start with Prabhi Patra. Your daily variables around 20 June seems out of phase for CO2 and others is true. Then this would be raise a bigger question whether the species scales of species analyzed match. For example, CO concentration may be affected by EAGWB, but the CO2 and CH4 have a greater influence of the far field than near field. Could you please clarify this question?
Yeah. Let me read the question once.
I mean, I can also try to explain you a little bit more if you want.
Yeah, please.
Yeah. So if you can, you remove your slide, but if you can go back to your slides, we can see that when
sure.
Like when you see that synoptic variability, there are out of page, and then also you showed that the CO2 and methane, the seasonal cycle is not matching, but of course it's not supposed to match because there are two different. Not this one. I am talking about other figure. The daily variability.
Oh, okay. Are you talking about this one?
Daily variability, not diurnal, daily, like day to day. Maybe previously, we slightly before. Earlier slide. Yeah, somewhere. Yeah, this one.
Yeah.
You see it around like a 20.
Hello, sir. Your voice is lost.
No, not this one. The other one, before. Anyway, so the thing is that you are not expected to see, I think, both CO2 but I think that linking this CO2 variability or methane variability directly to the agricultural waste burning or agricultural field locally maybe not so easy to explain.
Yeah.
Because CO2 has a very strong far field, because the ecosystem of the CO2 is so big in India, particularly northern India, that they will have impact by transport to the site.
Yes, sir, definitely.
And so that your agricultural field may have the maximum effect when the crop is building, like when the seeds are formed. But other times, the agricultural crop does not impact the CO2, for example.
No. Sure.
Because the mass is not accumulated at that time. The mass is accumulated when the seeds are formed.
Yeah.
So your CO2, and that's also related to Pramit's question before, is that so February and July, you see that July, August, you see that lowest CO2 concentration, because those are the formation of seed times for wheat. You see January, February is the seeding time.
Yes, sir.
So that your CO2 is drawn down by the seed formation, and same thing happening in the rice crop when this on that. The seeding happens in July, August, and in that time September. So your CO2 concentrations are lower. So they are not really like a whole cycle up. And then whenever that April, May, that time like all the things are dry and it's hot. So it's CO2 basically respirated from the ecosystem, and that dominates the region.
Yes, sir.
Something like that. So you have to be careful to interpret these things. Like also the methane, the hydroxyl radical loss is not local. It's a lifetime, like at least 1 year. So the time scale is at least 1 year.
Yeah.
So hydroxyl radical directly does not affect local concentration. It's a hemispheric mean concentration which is affected by the hydroxyl radical loss.
Yeah.
So you cannot explain your local variability by hydroxyl radical loss in that sense.
Yeah.
Yeah. So you have to be a bit careful on these explanations.
Yeah.
Yeah.
Thank you, sir.
Okay, and next question I'm moving to Pramit. Why is the CO2 concentration low in February? In fact, this is comparable in magnitude with the annually lowest value observed in June. Also, why do we see maximum CO2 concentration in spring in May?
So towards February, actually February starting onwards, the summer season starts here. So if you look at the boundary layer profile, monthly boundary layer profile, also there is a huge increase starting from towards the end of January to February. So the dip that we see could be basically due to the dilution effect, and the maximum concentration of CO2 that we see in May is actually due to wheat residue burning. So similar to what I have explained, the paddy residue burning in October, November months, we have the wheat residue burning towards the end of April and May. So that is contributing to the highest value of CO2 in the month of May. And if you look at the lowest values during July and August, it is very well coinciding with the vegetation index cycle or the NPV, primary productivity also, because after the onset of monsoon, the vegetation increases in large amount, and then it can act as a sink for CO2, which could be the reason why in July and August it is showing the low values when compared to the October or November, where it is high due to the crop residue burning.
Okay, so the next question is, so please keep your presentation. How do you account the cloud screening problem while taking the fire radiative power during monsoon period? What is the uncertainty? How it transpires to maximum estimates in the inventory, which is the pre-harvest estimate?
So the pre-harvest season is actually after the monsoon. It starts from October, September end to October, which is very clear period. So obviously when you consider the fire activity data for the distribution, so you will have to, that is one of the disadvantages of using the satellite data, because it won't be able to capture all the fires. There will be loss due to the haze and cloud cover. So that is the disadvantages we have to live with when you take satellite data. But we have used only for distribution. The emission was calculated from bottom-up method. So the emission quantification is purely based on the crop statistics. So the FRP should not affect the emission quantification. That is the advantage of using a hybrid emission inventory.
Okay. Next question is from Prashanjit Ghosh. Your calibration mixture is 3 times than ambient. Any specific reason why you prefer such high concentration? How do you discount possibility of emission from seasonal livestock migration important for this region? So
the reason why we have used high concentration is because when we also do the source samplings. So when you do source samplings, there is a limit to which you can dilute using zero air and the measure. So suppose if you are CRDS has a very large linearity range. So if you want to measure high concentrations, then you should be able to do calibrations up to that dynamic range. So if you want to do measurements of a source which goes up to 100 ppm of concentrations, then you should be having calibrations, a calibration standard of flexibility, so that you can dial it to that range and check the linearity for higher concentrations as well. So that is one of the reasons why we have calibration mixes with high concentrations. Yeah.
Okay. The next question is from Imran. What was the sampling altitude for CO2 measurement?
Sampling?
Altitude.
I did not understand.
What was the sampling altitude for CO2?
Oh, altitude. Sorry. Yeah. So these were all the inlets for like from the ground level, 20 meters above the ground level. That is where the inlets were located.
20 meter above the ground level.
Ground level, yes, sir.
AGL or ASL? What is it?
ASL.
Yes. Above sea level.
Okay, no, not above sea level. The Mohali region itself is 310 meter above the sea level, and from this ground region about 20. So if you calculate above sea level, it should be around 340 meter.
Okay, it is kept it on somewhere at the terrace or so, right?
Yeah.
Okay. And again, another question from Chaitanya Jain. When you did the measurements in the burning experiment, you are very close to the source, whether what is correct in reality, it is a mixed CO2 we talk about, not close to the emission source. How will it affect your emission inventories?
So in the emission inventory, we are particularly calculating from that particular source. So as close as we go to the point source, the emissions will be completely. So we want to identify what is the source contribution of biomass burning, particularly from that particular source. So as close we go, it is more accurate, I would say, because it cannot be compared to the whatever what we measure, because it undergoes a lot of chemistry and then transportation when we measure here. So the accuracy of the emission inventory would be good when we sample it from the point source.
Okay. So we have another question from Vinu Valsala. Attributing all the features of the season cycle to stubble bringing and local agriculture is not a good idea, in my view. Especially in April, May, the respiration of biosphere not locally, but on a large scale, also has high as compared to GPP. Example, other station India, which is not by direct influence of agriculture field, also show similar season cycle.
Yeah. So I agree, sir. I completely agree. I just wanted to here highlight the, especially during the high concentration that we observed in the particular months of October, November, and May. That is when the crop residue is active. So then I wanted to zoom into that. But the entire cycle, as you and the professor said, it is. I'm not attributing it to the crop cycle. Definitely not.
So AGL above ground level. Yeah. So we have another 5 more minutes for this presentation. So if anyone has any questions, please raise your hand, or maybe you can post it on chat. Yeah, Prashanjit, please. Yeah.
I think Prashanjit's not able to unmute. Let me work on it. Just hold on, Prashanjit, a minute.
So you can allow mic, I think it's in that case.
Yeah, we are allowing.
So before that, I have one question, Dr. Hasib. So when you make this emission database for biomass burning, because it is only that because you wanted to quantify the effect of the crop residue burning, because there are other sources is also affecting on the CO2 concentrations.
Yes, definitely.
So what is the point of only making up the emission inventories for crop residue burning?
No, actually we have already developed an emission inventory from road transport as well, and also from garbage burning as well. So I just wanted to highlight I was trying to highlight in these 2 months, if you consider the emissions from party residue burning, it is much higher, as I said, 25 times higher when compared to the other sectors which we have already quantified. So comparatively, the importance that we give to the paddy residue burning as a source of greenhouse gas should be highlighted in that way when you compare the source contributions. So I'm not particularly quantifying this particular paddy base alone, but we have developed implemented for other sectors as well and compared it with others.
So in that case, you should also needs to be taken into account of other influences also, apart from that anthropogenic influence, right?
Yeah, sure.
So can you have like a kind of a idea that how you are going to like separate out the influence of both, because you have a I think a few years of the data.
Yeah. So we need to look more into the data, as I said, the long-term data, and see what are the other sources that are contributing. This paddy residue is one of the most significant source, which is easily identifiable, and then it was the emission, as you have seen, it's much larger volume. But the other sources contributing around the region, the emission sources available around our region, we need to identify and see like a source apportionment study could be done to identify the contribution of different sectors and then quantify them later on. Yeah, it can be done with especially with such a long-term data. A source apportionment study can be done to identify more sectors, and then you can start the mitigation or whatever about it.
Okay, thank you. Now we move to what's the question?
Hasib, I will quickly ask, because one part of my question has not been put. So now, what do you think about the livestock? Because if you think of emission and you are saying inconsistency in your some kind of satellite-based observations with your observation, how do you think about the livestock migration? Because this is very common in regions like Haryana, where there are enough amount of cattle which are there.
Yes, sir. Actually. Yes, definitely, because we have actually done experiments like where we have gone to cattle fields, and also different cattle where methane emission is one of the most prominent from cattle fields. And then we have done experiments where we have gone to the field and measured emissions. We have seen high values from cattle also. It is definitely a highly contributing sector to greenhouse gas emissions, definitely.
Okay, does it have any seasonal variability based on your inventory experiment?
For identifying the seasonal variability, you need more to look into data, sir. So depending on the emission inventory, we cannot simply say.
Before you end, you measure CO2 using Picaro. So do you get also 13C in the same instrument, which you don't use?
No, sir. We do not have isotopic measurements. We just dry mole fraction and wet mole fraction only be measured.
Okay, thank you.
Okay, Dr. Hasib, we have a few more questions. A question from Deep here. How did you take care of the background concentration, for example, separating agricultural soil emissions and paddy burning?
So we have not separated the soil emissions, soil respiration emissions. We have not separated.
Oh, okay.
So for that, we need to do soil emission experiments, like we have to do that. From the ambient data, we cannot simply separate both those two.
So you want different kind of methodologies required to do that, right?
Yeah. We need to calculate the soil emission fluxes and then do that. Yeah.
Okay, so another question from Kavya Jeevan. For how much area the sample concentration can be extrapolated?
For what area? I do not understand by area.
For how much area?
This kind of footprint. How much is the footprint of the observations?
Yeah, maybe Shyam.
Like right now we have like over a region of. So if I say in terms of latitude and longitude, like 23 to 33 latitude, and then almost comparing.
No. I mean, like the area of which how much area, like by let's say up 10 kilometer radius or 100 kilometer radius, is a radius of means your sampling site, or your samples are like representing.
Oh, so this over the entire northwest Gangetic plain, you can consider as a regional representative. So basically, up to you can go up to Delhi to more than 200 kilometers.
Yeah, but how do you determine that? How do you say that?
Because like if you look at we get wind direction from all around the region, and also if you compare the seasonal variability of the meteorological parameters with the studies nearby, and you also from measurements we can see how representative it is.
No. I mean, that should be like a sensitivity test to calculate those things, because you can see how far your signal dilutes. For example, so for example, you emit something 100 kilometers away, but that will not be sampled at your site because it will get mixed and go somewhere else.
Yeah. So see, for greenhouse gases, you can also do back trajectory analysis because it is highly stable compound, long-lived species. So
But then again, you see that you are contradicting your results, because you are now assigning your local variability to the agricultural waste burning, which is happening nearby.
Yeah.
But then you are talking that you're telling that it's going out to Delhi. So I think they are two contradictory things, you see. So you are basically trying to say that it's all local effect in some sense, but then the footprint cannot be going up to Delhi. So
for that, basically, sir, we have to also analyze the air mass. We can look at the VOCs and see maybe the aging of the air mass can be done to see how far it is coming from by looking at the different ratios like Vincent to
yes,
ratio,
yes.
etc.
So
you have to do that air mass.
What to be done to?
Yeah,
to
that can be actually done. That can be actually done. So
yes.
So there was a point by like Pramit, they mean to say how much does your measurement see? That is the measurement footprint. Do you run any Lagrangian footprint model or to determine this?
No, not so far, sir. We have not done yet.
So you have a plan to do that, right?
Yeah. So I have just this is just a preliminary. I just started working on the greenhouse data. So we are now that we have enough data, we are looking at the long-term trends, etc. So we have planned to work on it.
Okay. So any questions?
So people ask him too many questions in 2 weeks time. Good.
Okay, if there were no questions, let us thank Dr. Asif Hakim for a nice and informative talk.
Yeah, sir. I also wanted to make a point that I also attended the first workshop greenhouse at Pune. So at the time I was in my PhD and I was working on VOCs. Even though I was performing the measurements of greenhouse gases, but my focus was on VOC measurements. But right now I have shifted to greenhouse gases, and then actually the workshop also motivated me to look more into the greenhouse gases. So I'm just starting. So hopefully with this workshop and the whatever knowledge I have got from the previous one, I can do some good analysis in the future. So I would like to thank all the organizers also for that.
Fantastic, yeah. So Pinu, I think we should make a list who attended the first one and second one.
Yeah, it's true.
So yeah, I'm just in the learning stage about the greenhouse gases and all. So I would like to participate in the next workshop as well, and then come up with more interesting analysis.
But maybe you are the organizer for the next one. Who knows?
Good point.
Yeah.
Right, Vinu?
Yeah, that's a good point.
Yeah. Okay, good, great.
Yeah. Okay. Thank you, Dr. Sivakin. Before moving to the next presenters, we will have a break for 10 minutes, right, Dr. Vinu?
Yes, Ravi, but during the break, you can
I'll ask the next
Atul to put up the slide and make it,
sure.
if any technical issues we can resolve.
Sure.
Yeah, thank you. Professor Atul is he's already logged in.
So the next presenter is Tiwari sir, but he is not in the case.
Oh, no, actually we shifted. Next Professor Jain Atul will present, and then Tiwari will take in the afternoon. Yeah.
Okay.
And next is a keynote. It's a 1 hour duration presentation.
1 hour duration. Okay, then.
Professor Atul, can you hear us?
Yes, I can.
Yeah.
Very good. Okay. Ravi,
so the only issue is I'm not sure how I am going to share my slides. I don't see option.
There is there's the video mic button bar, status bar you see at the bottom. So there is open share tree. That the third icon is open share tree.
Yeah.
Hold on. Where is I'm not able to.
So if you,
have you seen the
mic click
button
on the screen, one thing will pop up.
So there is a one turn camera off and turn mute, and then next is open share tray. If you can look at that symbol, you just click on that, it will share your.
Hold on. Presenter. Share contents.
Correct. So you click on that.
Here it says open share tray.
Me too.
So this presented mode. Okay, so I see that include computer sound. That's fine.
So Atul, do you see a square and an up arrow?
I just clicked that. It opens the window, right?
Yeah. Then yeah.
And but then how do I?
Just screen share. You can share entire screen or the PPT mode, whichever you want.
Okay, so let me do this actually. So I see screen.
Are you using from the Teams apps or you are using the website?
Website.
So should I share my screen or
yeah,
the
entire
file?
screen would be better. Share your entire screen. That would be the easiest. Yeah.
Screen is better. Hold on,
Yeah.
then hold on. Just can you hold this? Then I close all my other window to make sure.
Yeah, be careful about secrets.
No, it is going to be more convenient. It's not about the secret actually.
I'm joking. No,
it's about convenience only.
For handling.
Okay, now and so first I should turn on my camera, right?
You can.
Yes.
If it is possible. Can you see me now?
Yes.
Okay, more important is how to share the screen.
So there is
after the video, there is audio sign and the yeah.
Yeah, coming up. Yes. Go to your PPT, please.
Okay, now I am going to do this. This is my problem. So I don't see now anymore.
So now you can go to the PowerPoint and
how do I? Because this
is there an option?
Hold on.
Yeah, you open the PPT first, then you may do the same thing. So
Atul, are you in New Orleans?
Yes, I'm in New Orleans. So for me, it is around 11:30.
Oh.
But you're on a business trip, so you can.
Yeah, you're right. I haven't. Okay, anyway, it's fine.
Okay, we see your PowerPoint. Can you make it slideshow mode?
Yeah. But if
presentation mode?
Presentation mode.
Yes, please. Yeah, please keep it. Yeah, thank you.
Okay. So we have a 5 minutes break and we can join at 11.
You can start at 11. Yeah, 5 minutes.
Yeah, you can. But 5 minutes I think you can easily spend with Atul by talking about New Orleans. How is the AGU?
AGU is actually in a mess.
Oh,
it's empty or it's like still very crowded?
For hosting meeting actually.
So some 10,000 people came there now in person, right? Some 10,000 people attending in person, right?
It's about 8,000 people.
Okay, 8,000. Okay, still quite a lot.
Yeah, but if you may recall, in 2019, right?
Yeah.
There were about 27,000 people.
Yes.
So compared to that,
no. But last year 0. You imagine that?
Yes, you're right. So Prabhi, how are you doing?
Me?
Yes. I have a question about the inverse modeling results for our South Asia region. I believe now they have shared the model results. I should trust those model results, or you're going to provide me some model results?
I think you should. I think you should use my model results too, and then I can give you also CO2, methane, and N2O, all three.
Okay.
Yeah, I think we should have a separate meeting for this. I think with you and Masai also doing this analysis for Southeast Asia. So
you're right, but you remember that they have recently shared some inverse model results.
Yes. I can. I have made the plots. And I can show you another time.
So so those are your model results or
no,
me?
Probably not there in that list.
So why didn't you provide them also? So
you know the history of GCP, right? We talked about there is history and the problems and then the Bossidum and everything. So I think let's not talk here.
Okay, so others are also listening. Okay.
Yeah. So I think there's like a lot of things going on, and
you don't want to give the wrong impression to others. Okay, I get it. Okay.
Hello, Atul sir. How are you?
I'm doing fine. So it's a permit. Hi, how are you?
Yes, I'm also fine.
So Pramit is doing great, actually, right?
I don't know, sir. You have to tell. Pravitha has to tell him. I don't know. I'm trying to do my best, actually.
Yes, you're right.
Professor Atul, good morning. Good evening.
Hello, good morning. Yeah, good evening. Oh, it's a good night, actually. It's a midnight.
How are
it's
you?
going to be the next morning, actually.
Yeah, right. How are you?
I'm doing fine. How are you?
You're in AGU, right?
I am at HU, right? Yes. So I was thinking maybe visiting sometime India soon.
Sure. Yeah.
Sir, this is like I have never talked to you in the same position twice so far. Every time you are in a different location. You travel so much.
So,
sir, are you having IIT?
Yeah, good to see you after a long time.
Yes. So, is my camera on, or do I have to do something? Because it may be.
On. Your camera is on.
You are visible.
We can see you, yes.
Okay, good.
Atul sir, do you have a plan to IIT Delhi again, like last time?
No, no, not yet actually, because the situation is not so good. Actually, I don't want to be, quarantined in Delhi or maybe in the US now.
Right? I think last time it was 2019, like 2019, right? Like it's.
Oh, I did something. Okay. I hope this topic will be interesting to the audience. I'm not sure.
Yes, of course. I think there's no doubt about it, because yesterday also there is like a Professor Dhadwal gave a talk, and we had, and also Krishnan was there, director of IITM now.
Earlier
so
talk
we discussed a lot. I mean, they discussed a lot about discussing carbon, water, and food nexus. So I think you are right in time.
Great. And actually, the other earlier talk was also related to the. We have already, it's part of our study, rice emissions from rice burning part.
So this is very much in that line of the food and carbon nexus. And this is, I think, the only one which is talking explicitly about food. So
that's what I thought. Maybe it will be good for the audience, actually, something new.
No, it has to be. It's very important for us, I think.
Okay, great.
Okay, Ravi, I think it's 11. We can start.
Okay. Let us welcome Professor Atul K. Jain for this keynote talk. Professor Atul K. Jain is giving his talk on the quantifying food-related global greenhouse gas emissions. I would welcome Professor Atul K. Jain. Please, floor is yours.
Thank you very much, and good morning, everyone. I'm in New Orleans. For me, it's a good night, but I hope that I would be able to deliver the talk as I am expecting. Let's see. So this is the study about. I have lost my presentation screen.
Yes,
you lost your presentation screen.
Yeah.
For some reason or other.
No, it just is showing the Teams window. So
it was there. Then I'm not sure what happened.
Can you share it again and
in process follow the same process.
Okay, I don't know what's going to happen. So, okay, I may have to change. Okay, let me. Okay, I made a mistake. I'm sorry. It was always the issue with. Hold on. Okay, I think it's coming now.
Yeah, it is. Yeah.
Yes, sir. Yeah.
Okay, so actually the topic of my talk today is quantifying food-related greenhouse gas emissions. Again, somebody is doing something that's creating me a problem actually.
Okay. So
it's that's.
Yeah, it is up
so
again.
It's happening at your end, not my end actually. So
sir, are you using the app or the website? From website, it is better actually. From browser.
I'm using my app.
App can be problem sometimes.
No,
Okay,
I
anyway.
tried once. Can you go to the next slide? Just want to
Yes,
check.
I'm going. Okay.
Yeah.
So the title is quantifying food-related greenhouse gas emissions. Although we have actually, I'm actually looking at the global scale. So I will try my best to identify some of the important issues, or I would say the features which are important for the India region. But this study is a global study. Okay. And it's not moving further now. This is another issue actually. So I should not do this in my cursor is not moving. Okay, now just to go for actually my talk, I just want to briefly give some background about myself. And we have a very broad interest, research interest, not only looking at the food emissions, but also tracking at Earth's carbon nitrogen budget on land, impact of land cover land use change, and their impacts on the water, energy, and the carbon, and as well as nitrogen. We also studied northern high latitude, particularly looking at the permafrost soil carbon storage and how they are being impacted by the climate change, impact of growing bioenergy grasses and the biophysical and the biogeochemistry of the biofuels, methane emissions from the wetland and the uplands, and to emissions from the managed and unmanaged land. Not only the wetland, but also the upland as well. Climate impact on the agriculture and the food supply, which is the topic of my today's talk. Okay, and we do this research by using the models which are being developed by my students and the postdoc in my research lab, and also combine that model with the satellite and the ground-based measurements, and study the interactions of land and atmosphere using these models and the data. Eventually, we are interested to particularly actually study, the human aspects, how the humans are impacting our biophysical system. So we are not only developing the land atmosphere model like ISAM, but we are coupling those with the Earth system model to study the interactions. And then we couple also with the socioeconomic and human dimension component to study the interactions of the biophysical and the human aspect. So that's eventually our research interest. Okay, so this study has recently been published in Nature Food, and most of the results which I'm going to present is based on this study. And this study was led by my group members, particularly the research scientists in my group, Xiaomin Xu, and other grad students, Pratik, Shije, Tishon, and also in collaboration with Philippe in France, and Francisco Tubilio from FAO, Pete Smith from England, and Nelson Campbell is in the US. Okay, just to give you some brief information, this paper, when we published, I was not expecting to get such a wide, coverage, but based on the Altimetrics, the metrics, I think this is a widely cited and covered research article. And you could get a lot of information about our research article, not only the positive, the comment, but also there are many other aspects of these issues which have been discussed in widely in media actually. So you could actually go to this Altimetrics site, and then you can look at different, the coverage. So this study is actually looking at only the one sector of the total emissions, that is the food sector, which is one of the components of the agriculture, forestry, and other land use component of IPCC estimated total greenhouse gas emissions. And this figure we borrowed from IPCC, the last assessment, not the most recent assessment. And according to that assessment, total greenhouse gas emissions from all the sectors were about 50 gigatons of CO2 equivalent, in equivalent in the sense for all the gases, not only the carbon dioxide, but also the methane and nitrous oxide as well. And the food sector is one of the subcomponents of this AFOLU. And according to IPCC, the last assessment report, the food sector contributed, particularly the agriculture. In 2010, about 12%, 10 to 12% of the total greenhouse gas emissions, which is 5 to 6 gigatons of CO2 equivalent. And this component also includes the land cover and land use change activities, which contributed about 9 to 11%. Just to give you some background about the units, which I'm going to use in this my presentation. So 1 gigaton is equal to about 1 petagram, okay, or about 1,000 trillion gram or 10 to the power 15 gram. So it is a big number, okay? And CO2 equivalent represents the CO2 equivalent combined of all gases, including carbon dioxide, which is the major one, methane and nitrous oxide. Okay, so before I go for the food sector emissions, I really would like to give some brief background about what are the contributing factors to the food sector emissions. Okay, so you can think of as a farm, and all the activities which occur on the farm contribute to the emissions, not only the sources, but also the sink. So for net primary productive, which is a sink, right? All the carbon which is being stored due to the the photosynthesis is a sink, but there are many other activities occur at a farm level. You can think of as a one single the agriculture farm, and you can expand and you can actually calculate the emissions for entire the city, the region, and then this country, and then actually the global. So you can think of as a farm, and what almost all the activity which occur at the farm contribute to the emissions of greenhouse gas emissions. For example, if farmers want to expand that land and cut the forest, and almost all the carbon which is being stored in the forest, it is shown here, right, would release back to the atmosphere. Not all. Part of it will be left on the ground as a litter and can be stored in the soil. So you see the two kinds of arrows. One is going downward, which is actually you could consider as a sink. So harvest of the forest, the wood can be used for the products, and the carbon could remain in this product pools, right? But the litter fall on the ground could become a part of the soil, or rest of, then depending on the soil turnover time can release back to the atmosphere. But the crop residue and other agriculture residue can be burned and release greenhouse gases, including methane, nitrous oxide, carbon dioxide, carbon monoxide, as well as non-methane hydrocarbon. And all the livestock activities, the animal graze on the land, and they actually left their the waste on the ground, that become part of a manure, and that also release carbon or methane, and part of it can be actually goes as a part of this, the fertilizer, which we call the organic fertilizer, right? Humans also apply, or the farmers also apply the inorganic nitrogen and release N2O. So that is a part of the fertilizer. And all the farmland, the machinery also release emissions, right? And they also part of for the plowing the land or tilling the land, moving the agriculture product from one place to the other. All these activity also contribute to the emissions. So fossil fuel emissions, which is being consumed by these machinery, also become a part of emissions, as well as the rice paddies actually has a quite unique features. They not only release N2O, but majorly they release methane also. Okay. In addition to the farmland activities, there are other activities beyond farm gates. Farm gate activities. They also contribute a lot to the emissions to the food sector. For example, the fertilizer which the farmers apply, nitrogen, maybe the phosphorus, they are mined, then manufactured, and then transported to the farm, right? And they also contribute emissions, right? And once the product is being harvested, then it is processed and they also contribute the emissions. So our actually study account for all these activities you can think of at a farm level, then you can actually extend it to the global scale, combining all the farms in the world, or you can think country and then and region and as well as the world. Okay. So when we talk about the plant-based agriculture as well as the animal-based agriculture, so what we mean by that is that plant-based agriculture emissions is released when the crops are produced for human consumptions, right? And animal-based emissions are released when the crops are produced for animal feed, right? But also at the same time, the grazing land is being maintained and used to, feed also to the animals. Seafood also contribute to the emissions, but in our study, we have not accounted that particular emissions, okay? So to give you an idea about some very basic idea that to produce, the animal-based emissions have a larger emission intensity than the plant-based food emissions intensity. For example, wheat has an emission intensity of about 2 kg CO2 equivalent per kg. So for producing 1 kg, about 2 kilogram of CO2 is released. Similarly, to produce a 1 kg of animal-based food, particularly the beef or the pork, actually has a carbon intensity of about 67. So you can see that the carbon intensity for the same amount of food is much higher for the animal-based food than for the plant-based food. I just want to give you the 67 come from the beef. I know that we don't eat beef. I'm a purely vegetarian, but just for giving that information about comparing the emissions, I'm just giving this number. So pork has about 10 kg, and also the chicken has a much less, about 6 or 7. So these have different intensity. Okay. Okay, so in this study, we have built a system, what we call the model data integration framework, to study the emissions from the plant-based and the animal-based production food. Okay, and particularly we implemented land management practices in our land surface model. Okay, almost all the activities which I have discussed so far are part of this land surface model, and we are studying three major emissions from the three major greenhouse gases: carbon dioxide, methane, and nitrous oxide, from the production as well as for the consumption. So you could think of that not all the food produced is consumed at the same place. So for example, actually in the US, perhaps in India and other countries also, most of the food produced is consumed in India itself, but part of it is also being imported or exported. Similarly, so we are not only considering study the production-based emissions, but also the consumption-based emissions. Okay, and we have looked at it not on a gross scale, but also subsector. So subsector at a local, regional, and the global scale. Okay. Particularly, this is very interesting that we have tried to consider almost all the crops which are grown, approximately 170 different crop types, and also 16 animal products and used in our study. We calculate the net emissions. So as I have shown this figure, you have arrows, release to the atmosphere, and also the sequestering in the plants, like in the photosynthesis in the soil. So when I talk about the emissions, in our case, emissions are the net emission for each sector. Okay, for example, somebody would say you that, oh, soil emissions are very high, right? But that is not a net. So when we report the net emissions, although we calculate the gross emissions for each individual activity, but our emissions are the net emissions. And some of the advantages or advances of our study includes explicit attributes of the total food greenhouse gas emissions, from plant and animal base. We are accounting for the impacts of most of the important environmental factors such as climate change, carbon dioxide, and also the direct human activities such as land cover and land use change. So in our case, any activity, agriculture activity occurred due to the land cover land use change contributing. So we separated the land cover land use change and then report as a separate sector. But this land cover land use change only consider agriculture. So if forest is cleared for agricultural land, cropland or pasture, in this study we account for that component of the land cover land use change. And we also account for the feedbacks. So our system is a integrated system. So we account for the interactions between these gases, carbon dioxide, nitrogen oxide, methane. For example, you can think of the nitrogen emissions or nitrogen application can have a limitation on the plants, and that can control the carbon emissions, for example. So we are considering actually the interactive feedback between the three different gases. So, and also have a detailed representation of the land management practices, particularly the carbon and nitrogen methane dynamics. For example, we get the livestock feed from the agriculture and then part of that return back to the agricultural land as a manure. So it is a complete cycle. We account for this cycle. Okay, so as I have mentioned, we are considering the 4 different sectors. One is the beyond farm gate sectors, as I've already discussed, including the mining, manufacturing, transportation of fertilizers and the pesticides and food processing, farmland activities, including the farm practices such as tilling the soil, planting crops, irrigation, harvesting grains, and recovering crop residue, which become part of the feed. And land cover land use change, cropland and grazing land, and then livestock, including anaerobic fermentation and the manure management. So in case of land cover land use change emissions, we clear the forest or the land, and the part of that wood goes to different product pools to make products such as furniture or paper products or other products, and then also the land is disturbed due to the land cover, and we consider all these activities. In case of the farmland activity, there are many actually activities. For example, the photosynthesis is fix the carbon, and here positive is the source and negative is the sink. And then that part of this grown biomass is being harvested for grazing and also for recovering of crop residue, which goes as a feed. Okay, and the farmers also till the land, so we also consider that emissions, and also biomass burn, right? And not all the the biomass remain on the ground, and we burn. And the previous talk was related to this topic about left biomass burn. Actually, I believe I could not attend, but I believe so. We also account for that component as well. Okay, so in case of crop and grain, there are 2 components. We carefully look at it. So just I want to make sure that granularity is a very important in our study. Not only local scale, what happened at a plant, at each individual plant, but also at a spatial and the temporal scale. So just to give you an idea about at a plant what happened. So when we harvest the crop and crop grain and also the residue. So crop grain could become part of the plant-based, the human food. It could go to the livestock feed, and it also has been used for other utilization. For example, the rubber, the paper, rubber plants, and also cotton and biofuel. And the residue part of it is burned and left on the ground as a litter. But part is also used as a feed, so crop feed, right? And that is also we keep track of. Okay, so the livestock feed biomass is very important, and because not all the animal eats the same feed, we have to be very careful about what does the monogastric and other the other animals, ruminants, eat. So we keep track of different kinds of feed. and we calculate the feed per animal head and how much they required. And then we also keep track of manure produce rates based on the feed, right? And we define the feed into different categories because crop grain feed and the other forage is being eaten by or fed to the monogastric, and the rest goes to the ruminant. So the numbers which I'm showing here is for the global total, the feed amount. It's not the emissions, it is the total feed which we harvest from the agriculture product. Okay, so this is about total I will show in the next slide the country scale. You could see how much is coming from from different countries, but the total crop feed is about 2,450 trillion gram of carbon per year, and this is based on the region, right, as well as for for the country scale, which is plotted as a 30-minute resolution. And one could see that how much is a contribution for India and also for China and Mongolia. These are the two major, Southeast Asian country contributing most of the, the animal and plant-based emissions, but also the South America as well, including mainly the Brazil. Okay. As I have said, this is a very important thing that we have considered the management cycle. So whatever we have the crop, grain, and the feed, which release carbon and then being fed to to livestock, and they also have carbon and as well as methane in terms of carbon, right? And we keep track of also how much is the methane emissions when it's fed. And actually the product is being used to produce the milk and other the animal products. Okay, mainly the milk products, and also the waste goes as a manure, right, and which is left on the grazing land and processed and applied to the cropland. And the nitrogen have two different, manure nitrogen has two different forms, organic and inorganic. Organic goes to the soil, inorganic is being actually denitrified and become part of the nitrogen. And the manure carbon is organic, which returns back to the agriculture land and treat it as a leader in the model. So we keep track of all this component as a complete cycle, and we have a budget, we have a conservation of carbon, mass, and nitrogen. Okay, so this is just the the schematic diagram for our land model, particularly for the soil. It has a different, it has a different soil layer, goes up to the 3.5 meter, and actually calculates a different, the processes. I don't want to get into more detail about this. One can look at in the paper to give some better idea about the model description, but it is quite detailed and including most of the important processes. We calibrated the model with the C14 and turnover time of soil recently, and so it is quite detailed, the soil and component of land surface model. And again, methane emissions for agriculture, particularly for the rice paddies, calculated again is quite a detailed model. We separated in this model, the wetland, non-wetland, and non-wetland actually all the agriculture components come in the non-wetland. There are many processes are considered. So this model has the same, the soil component. It goes up to 3.5 meter, and we separated this 3.5 different layer, anaerobic and aerobic, condition depending on the oxygen, and the model calculates the oxygen amount. So one could look at it, the anaerobic conditions would have a much higher emissions depending on the layers as well as depending on the regions as well. Okay. And similarly, we also have a quite detailed N2 emissions model. I don't want to go in again depth, but the most of the N2 emissions come from the fertilizer application in the case of agriculture. Then we calculated and calibrated the biomass, which is becoming part of the emissions for different crops, about 171 crops on a global scale. Here we have compared and evaluated our results with some existing data. And then similarly, we did this for methane emissions. I'm showing here for South and Southeast Asia. We compared our model results shown in the blue with other studies. South and Southeast Asia, as you could see for India, the emissions are the highest for methane. And I'm not surprised, mainly because the rice production is the highest in South and Southeast Asia, mainly in India. I'll discuss this later. Okay, and similarly, we did this evaluation or calibration for N2 emissions as well from crop grazing and other ecosystems. Okay. Now, in case of consumption-based emissions, we also do that, but the consumption-based emissions actually is reported on a country scale rather than the spatial scale. Reason being that it's very difficult to pinpoint the consumption, the export and import at a grid scale. We also only have the numbers at a country scale. So the consumption include the production, which I have so far discussed, and also the storage, which we call the stock variations, and import and export. Okay, here the C is the country and N is the crop. So we keep track of all the crops, as I mentioned, import and export of each individual crops. So as I have mentioned that we do this at a grid scale level, then we upscale it to country scale and then to the regional scale. And these are our, the various regions. So I'm going to report and results, some of the results at a grid scale level, but most of the results at a regional scale. So we divided this country into different, regions, including North America, South America, and Eastern Europe, European countries, Mid East and North Africa, MENA, Sub-Sahara Africa, Commonwealth and independent states, including Russia, China and Mongolia is in one country, South and Southeast Asia, including India and other Eastern Asian countries, and then Oceania and other East Asia, including Australia and New Zealand. Okay, so these are the total emissions. So, although we calculate the emissions for each individual gas, but we combine in the equivalent form using the global warming potential, which we use based on the AR5. And the global total food-related emissions based on our study are about 17,000 trillion gram of CO2 or 17,000 gigatons of CO2, which is approximately 30% of the total emissions. 49, if you may recall the 49, I have reported. So here is about 17, so which is about 30%. But still 61% of the emissions come from the CO2. Okay, so we still have to deal with the CO2 emissions. 27% from methane and 12% from N2 on a global scale. Out of this 61, 19% based on the plant-based and 32% based on the animal-based CO2 emissions. In case of methane, about 6% from the plant-based and 24% from the animal-based, particularly from enteric fermentation. And in the case of N2, 4 and 6% come from plant and animal-based. Okay, here I'm showing by sector. Okay, so what I'm showing here, the circles which show the size of annual quantities of the greenhouse gas emissions, and there are filled circles and the empty circles. So the empty and dotted circles are the sink, and the rest of the filled circles are the source. Okay, and the size would tell you about the size of the emissions. Okay, so in the case of plant-based emissions, the two major components contributing to the plant-based emissions are land use changes for the cropland and farmland activities. Okay, they contribute the most to the plant-based emissions. Product processing is also contributing, but comparatively less emissions. Fertilizer application also. There are some sink due to the variations, stock variation, but that storage is less. Okay, now you compare the plant-based and the animal-based emissions. There are many activities in the case of animal-based than the plant-based. As you could see, animal-based food requires both cropland and pasture land, right? And the land is clear for cropland and the pasture land, right? and also or grazing land, I would say, right? And the farmland contribute the most in case of the animal base. On top of that, the fermentation or animal emissions are also contributing greenhouse gas emission, which come from the animal's stomach or the guts, mainly the methane emissions, as well as CO2 release, respiration part. Other emissions are also contributing, but the factors are fertilizer products and transportation, but their contribution is much less. But the most important thing, which I also said, that intensity for animal-based, the product emissions is much higher, mainly because there are more activities actually to produce the animal-based food than for the plant-based. That's the major cause of higher emissions from the animal-based emissions. Okay, another important aspect is the land. How much is the land we are using to produce plant and animal-based food? It's total about 4,600 mega hectare of land we are currently using, which is about 30% of the total land. 30% of that, 31% is used for cropland, and the 70% is the grazing land. Approximately 42% of the cropland is used for plant-based emissions. 25% of the cropland is used for the animal-based. The rest is used for the other utilization. For example, as I have mentioned, for the other, the other products we use plant, for example, rubber and also the cotton and maybe other biofuels. So 70% of the land is used as a grazing land. All goes in the animal-based food, and you could see. So here you could see that plant-based food land is about 595 mega hectare, and then animal-based combined 345 plus 3,281. And other utilization has a 453. So these are the contributing total emissions by regions. Okay, I believe I have still 30 minutes, right? Okay, so these are the total emissions by region. So South and Southeast Asia is the first column, then South America, China and Mongolia, North America, Eastern European countries. And then we have Sub-Sahara Africa, SSA, and then we have CIS, which is Commonwealth Independent States, including Russia, and then Oceania, and then Middle East and North Africa, which is MENA. And one could see that South and Southeast Asia have emitted the greatest food. So here, the food production is by the blue. Okay, this is by the animal, and then the green one is for the other utilization. And one could see the South and Southeast Asia have emitted the greatest food production, right? This part, okay. Food-related emissions, approximately total emission is about 23% of the total emission, combining all the three categories, the plant-based, animal-based, and others. But the food production from plant-based is the highest for South and Southeast Asia. South and Southeast Asia also has the highest per capita emissions, right? Highest lowest per capita emissions, but highest per area emissions. Okay. This is
can I ask you a question here?
Sure.
Yeah, just want to make sure that what is the time period you used for these estimations?
Okay, I forgot to mention. Yes, I'm sorry. This is for the mean for the 2007 and 2013, and we are reporting here for circa 2010.
Thank you.
Okay, because that is the emission reported in actually AR5. So we stick to the 2010. And our all emissions are actually compared to 49 trillion gram of CO2, which I mentioned CO2 equivalent in the earlier slides. So, okay, sorry, I should have mentioned this. This is for 2010, right? So here I'm showing you per capita is the emission is the least for South and Southeast Asia, but per unit emissions are higher. And the second largest region contributing the most emissions are the South America. Okay, by the way, I forgot to mention, I think I've already stated about this. This is the only country which has the highest plant-based emissions, South and Southeast Asia. South America is the second largest emitter, approximately 20% of the total emissions to the global total, contributing by the South America. And it is also has the largest emission from the animal-based food. And one could see that these are the animal-based from South America. And also South America has the highest per capita emissions as well, as one could see this in this figure as well. Okay, North America, where we live, actually has also the fourth largest emitter. Okay, but in terms of the per capita, it is the second largest. In terms of per area, it is relatively low. Okay, so this is greenhouse gas emissions by food at a spatial scale. I have these numbers to show that for my city, how much are the emissions for my state in the US and for my country. But here I'm going to report all the countries, and I can talk a little bit more about the India and other countries' contribution. And one could see that South and Southeast Asia and China and Mongolia are the top emitting, the regions for the plant-based emissions, right? And they are contributing approximately 11% and the 6% of the total emissions. And in these regions, China, India, Indonesia are the countries with the most greenhouse gas emissions from the plant-based food, and they are contributing about 7%, China, 4% India, and 2% Indonesia of the total global emissions. In the case of animal-based emissions, the most prominent animal-based emissions emitting region is, South America, right? And they are contributing about 14% of the total greenhouse gas emissions. Then South and Southeast Asia, including India, right? And also China and Mongolia. Okay, so these are the three major regions contributing the most to the animal-based food emissions. And by country, China is contributing about 8%, Brazil about 6%, the US 5%, and India is 4%. Okay, so India is also contributing about 4% to the animal-based food. Okay, so these are the emissions from food production at a country scale, and one could see China, India, these are the total emissions, China, India, and then Brazil, the US are the four major producing countries, and they are contributing the most, right? And in case of plant-based, again, Brazil, China, Canada, India also, right? And also Russia and other states in that region are contributing the most plant-based emissions. Okay, so animal-based is mainly China, then India, also US, Brazil, these are the countries. So one could look also the subsectors. The farm emissions come mainly from, plant-based, from China, actually both plant and animal based from these countries, China, India, again, the same four countries contributing the most. Land cover, land use change, China is the most, and then Brazil. In case of animal based, this is for the plant based, this is for animal based, mainly China, and also, other Commonwealth independent states, including Russia. In case of animal-based, farmland activities, beyond farm gate, sorry. This is a beyond farm gate, mainly China, and other countries are not contributing more. And this is from the livestock. Again, livestock is only, there's not much plant-based for the livestock. So it's also, again, China, India. These are the major countries which are contributing the most, actually. Okay, one could look also the plant-based food emissions by the commodities. So rice is the major actually contributed to the greenhouse gas emission on a global scale. 12% of the total emissions come from the rice paddies, then wheat 5%. By the way, wheat has the highest harvested area on a global scale, actually, in terms of the plant-based commodities. Actually, the one important thing about the rice is that the two regions which I have discussed, South and Southeast Asia, China and Mongolia, are the most, they produce the most of the rice. About 90% of the total rice is produced in these two regions. So they contributing the most of the methane emissions, from the rice paddies. Okay. In case of animal-based food, beef contributing the most. Actually, this was the hot, actually the news when our paper was published. About 25% after our paper was published, many countries are now seriously considering to control the beef emissions, and they may switch to some other animal-based food. Cow milk and produce the next emissions, next highest emissions, about net 10%, and India is one of the largest producer of this emissions for cow-based milk. Pork is the third largest commodity in terms of the animal-based food. Okay, so these are some of the emissions actually for the export and import. The EU has the highest import, and so import is on the right hand side, export is on the left hand side, right? And the plant-based is blue, and animal-based is in the orange. And the EU is contributing or importing and exporting the most of the food, in fact, within European countries, but also from other countries outside the European Union. Then South America is also actually exporting a lot of actually food, because most of the animal-based food in the North America comes from the South America, beef and other kind of products actually. In North America, yes, okay. So you could see now in Australia and New Zealand also export and import a lot of animal-based food. South and Southeast Asia, one could see most of the food is being consumed in the same countries, but also they export animal-based food. Their production for animal-based food is the largest, as I have mentioned. So they also export a lot, These are the actually carbon flux in the feed manure cycle. So we keep track of each category. These are input, not emissions. So how much is the animal respiration, manure carbon products, and also the anaerobic fermentation. So these are by countries. North America, South America is the highest, because of they have a lot of beef and production in that country. They contributed the most. South and Southeast Asia is also, in fact, actually manure. Animal products goes back to the agricultural land, as well as respiration as well. Okay, so these are the feed to livestock products conversion coefficients, the efficiency, how much is the product is being actually is efficiency in terms of the biomass. In case of the biomass, it's only about 5%. In case of calories, about 6%. In case of protein, it's about 9%, 8.5%. And the least actually efficient region is Africa, and one could see that actually. And in case of the biomass and calories, also South America as well. Overall summary, I could say that global greenhouse gas emissions from production of food were found to be approximately 17,000 kilogram of CO2, which is approximately 57%, of which about 57% come from the animal base, and about 29% come from the plant base. So which is approximately half of the total animal-based food. And the rest 14% come from the other utilization. Farmland management and the land use change represents the most the shares of total greenhouse gas emissions. They contribute approximately 38% and 29% of the total greenhouse gas emissions. Rice and beef were the largest contributing plant and animal-based commodities. 12%, they contribute to approximately 12% and 25%. And South and Southeast Asia and South America were the largest emitter of production-based food. So South and Southeast Asia produce the most plant-based emissions. They're the highest actually, and South America is producing the highest amount of animal-based food. Okay, so there is a lot of discussion about what we could do to control the greenhouse gas emissions, okay, particularly from the animal-based food. So there are two ways we can control. One is from the production side, another is from the consumption side. Most of our study has focused on the production, so I can talk a lot more about what are the mitigation options available to us. Some of these mitigation options we have already availed and implemented in the model. Particularly, we can increase the soil organic matter by no-tilling the land. This is very powerful management practice applied most of the developed countries. And also we can think of managing the plant dates. Particularly the advanced technology can help us to improve the planting dates, and we can increase the planting dates, and we can have a higher production of food. So it will help to reduce the land cover land use change activities. Another management activities we can think of is precision fertilizer management, and that right amount at the right time application could reduce a lot of N2 emissions. And there are also some more advanced, now technologies which are producing methane inhibitors, which in fact their chemicals can be added to the animal feeds, which controls the methane emissions. In case of the consumption base, obviously the major option for us to control the consumption base food emissions is dietary changes, right? Instead of eating high intensity food, we can think of low intensity food. For example, you can think of actually beef to chicken, that going to reduce a lot of emissions. And also managing the food waste, reduce food waste, packaging reduction, new ways of selling, direct sale rather than through the third party. And all these options are available to us to control the greenhouse gas emissions from the food sector. Some of these options we are already studying in our research lab, and others we are interested to explore in the near future. Thank you. Just to acknowledge my co-authors, in the top is my team, myself, my student and postdoc, and then my collaborators, Felipe, Francisco from FAO, Pete Smith from University of Aberdeen in UK, and Nelson Campbell from PlantPure, public sector company, CEO. Thank you. I'd be happy to answer any questions.
Right. Now the floor is open for questions. Let me see if any questions. Yeah, let me start with a question from Aman. Does your GHG emission calculations from plant and animal-based fluid include respiration or perspiration?
Yes. As I mentioned, yes.
Evapotranspiration from plants and animal as well.
Yes, we include everything.
Everything.
Yes.
Another question from.
Before we move,
so as I have mentioned, we include emissions from animals, carbon emissions, methane emissions as well, right? Animal respiration we include. Also, we include the respiration from the plants, as well as from the soil. All emissions have been considered.
No, I'm just curious, like what Aman mean by the perspiration, even evapotranspiration in this case.
Yeah, it's
evapotranspiration means evaporation is from the soil. I believe the transpiration is from the plant.
Yeah, but
evapotranspiration is not a carbon, but
mobilizing component. They don't mobilize carbon.
So it is. You are right. It's not evapotranspiration. Is not emissions, but it's moisture actually goes in that.
Yeah. So this is not carbon. Right? Perspiration also same. It's not carbon.
Soil carbon. Yes. Mm-hmm.
Okay, the next question by Prabir. Why do you include animal respiration in GHG budget? Because that is the just cycling of carbon. Does this include human respiration as well?
Yes, we have actually, because we have to have a balance of the budget, right? So it's not only about the release from the other humans also release carbon. So we also account for all the emissions, but human emissions are very small. Actually, it's part of our carbon cycle. Actually,
yes,
we not directly account for. We indirectly account for.
I mean, you assimilate carbon, but you then release the same carbon by respiration. Like as much as food you take,
that's
basically
right.
You are respirating the same amount by the same amount of carbon by the respiration. So it's like a zero balance in the sense, unless you are growing fatter.
Zero balance in case of in a animal base, but in case of humans, it's almost zero balance, right?
Yeah.
Because animals also have a methane, right? So it's contributing. I can give you the numbers if you want. Actually, it is cited in our paper. I don't recall the numbers, but we have for animal base, right?
Okay, we will move to the next question by Pramit. Are these estimates at the source, that is the production zone, or at the point of user, that is the consumption?
Okay, as I have mentioned, our emissions are the net. I'm not sure what Pramit mean by the source. Because for each activity we calculate the net. What I'm talking about the production means there are two categories: the production emissions and the consumption emissions. What I mean by production emissions are the same, but one come from the how much is the emissions from producing the food, right? But in case of the consumption, we also have to account for the export and import, right? So we have to subtract the export amount, we have to add the import. So emissions you produces at one region, right? So we have to bring, if we are importing, we have to add those emissions in a country which is importing that emissions.
Yeah, actually, that was my question. I mean, I tried to rephrase the question in the second comment, like in this detail, what you explained right now.
I don't see the comment, but I can only hear the comment which has been read by.
Yeah, so my question, you have just answered my question. It was, if a country produces some food, be it animal-based or plant-based, and then it exports to some another country where it is consumed, so where are the emissions accounted for?
As I have said, that consumption base, if you look at the consumption base, include production minus export plus import.
Okay, you just explained it.
Yeah. Okay.
I have shown you the slide showing this net emissions for consumption base, which include 4 terms. One is production plus storage, from the previous year, and the export, which is minus, and import is positive. That is a net.
So I'm just curious, like how detailed you did this, because if you talk about storage, then you have the cold storage and that consumes electricity.
Yes.
So how far?
How far have you? So we have a quite detailed. We can provide you the numbers if you want. The storage amount is not much. It's almost negligible. It's not that much, less than 1%.
Okay, thank you.
Okay, the next question is by Prashanjit Ghosh. Do you think soil acts as a source or sink for GHG? How does that vary?
Okay, right. This is a very good question. So there are some direct source of from the soil when the land cover land use change occur. The soil is tilled, so directly the emissions goes up in the atmosphere. But then the soil become, the little part which becomes the sink, right? And depending on the turnover time of the soil. So the net emissions from the soil is not that large. Okay. I think I would not say not large, but it's about, I think 12%. I think the release is approximately 12% of gross actually. But I would not say it's a net, it's a gross, because as I said, in our case, we don't actually report as, as individual category, we only report as a net. Okay, so the total release from the soil is approximately 10 to 12%, if I recall that, as a gross emissions.
And the continuation of that question, how does that vary across latitude due to agriculture practices?
You mean the emissions?
I mean this source and sinks, like he's saying that the soil
one could see, I think one could see that actually. I can share that figure again. How do I do this actually? Can I do this? Can I share this? How do I do this? I'm unable to do this now. But unfortunately, let me tell you, you can think of there are 3 different regions, right, which are contributing, 4 different regions which are contributing the most. One is the South and Southeast Asia, which is in South, which is in the tropical region, right? And also, and the China and Mongolia, right? And then in tropical region, most, South America also comes, tropical South America, they are also contributing the most. And then subtropical region comes actually, North America comes in subtropical region. So I could say, and most of the emissions come from the tropical regions, so from the tropical countries. The next contributing region is a subtropical region. Make sense? Have I answered this question?
Prashanjit, he's not.
Yeah, so yeah, I think that this is quite satisfactory, but my intention was to understand that the agricultural practices where they use organic fertilizer compared to using.
Yes, so
yeah,
the
so
most
now
fertilizer is used in South and Southeast Asia.
Okay, yeah.
And in China is actually, they are overusing the fertilizer application. So the N2 emissions the most. Oh, I'm sorry, I have a figure. I because of the limited time I could not show. I have a figure for N2 emissions as well as for methane emissions. If you guys are interested, I could share later that emission.
Sir, so in continuation to what Professor Ghosh asked, actually, I have a question. Like, I want to understand one thing from the scientific perspective. That once you consider the manure in your presentation, you consider the manure in your budget actually there. So that manure, when it goes to the soil, so does this alter the C/N ratio and the microbial decomposition, or how does it affect?
Yes. In fact, actually, manure become is a kind of net sink rather than source, because most of the manure is organic carbon and actually which decompose very slowly, and also it provides nitrogen at a slow rate. That is why the manure is actually acting as a net sink rather than source.
Okay, thank you.
Okay, the next question is by Yogesh Tiwari. Animal food-based emissions over India are more than Europe. Is it due to more beef is eaten in India, or is it?
I don't want to go in this controversial issue, but I think unfortunately India is producing a lot of beef, actually, based on our study, and it is one of the major contributing factor actually.
I think that is a continuation of the another question. It says that India is the 4th largest export of beef. What should be done to decrease the animal-based emissions? Should the export be minimized?
Or we have bad practices, Professor Atul, in India.
I believe you guys have already answered your own question. Yes, right? Yeah.
No,
what you have to do.
I was saying, if we have a bad practices while handling such foods in India, so more emissions.
Yeah, of course, this is the major issue, but not only export, but also I think consumption is also a lot actually. Production is there, right? But some of the consumption is also there. I could give you the numbers, but I have not reported here because of the sensitivity of this issue for India.
But I think you also need to also, I mean, Yogesh too, the population is also very large, right? So you're comparing two different population size.
I agree. I completely agree. The two regions which is the highest population are India and China, and these two contributing the most. But I was a bit surprised to see that animal-based food production is quite a lot actually, because I thought India is most of the Indians follow vegetarianism, including me. I used to, I'm still pure vegetarian, but I was a bit surprised to see that the emissions are quite large. Not only chicken, but also high intensity, animal-based food is also being consumed a lot actually in India.
So do you have any regional estimate, particularly over India, about emissions?
Yeah. I mean, as I have said, our numbers are gridded basis. So at 30, at half degree, we can give you for each individual product emissions for India, for each individual in the commodities, 16 different commodities for India, as well as for 170 different crops if they are grown in India. We can provide by the commodities. We have all the numbers. I'm not reporting here, but I'm reporting only the major commodities, like for example, rice, and the wheat and other major plant-based commodity. Similarly, the 10 top commodities, but we have number for each individual commodity. Everything, we keep track of everything at each grid cell.
No, but Utul, when you do this calculation, but you are also considering the methane emission from the enteric fermentation, right?
Yes.
So it is not to be consumed for the beef. So I think it will be also very careful there, because a lot of emission happens for the animals by the methane emissions, and they are for the living animals.
I'm not saying we are consuming beef. If it is consumed, okay, think of it is consumed. If the plant, okay, so let me try to clarify your point.
Yeah.
If the food, as I have said, we have a plant-based and animal-based production and the consumption. If the food is exported, we don't account for the country's contribution to that part, right? We
subtract methane emissions
too, everything. Methane emissions too, even soil emissions too, everything.
No, but how do you export the exportation? Methane emission has no export.
No, methane emissions is not, but methane not food production is. So we keep track of food. So how much is food, for example, how much is actually beef is exported. So for each plant, each cow, how much is the methane emissions? We can calculate, right? And how much is per food in terms of kg is the emissions, as I have mentioned about the intensity, right? So 1 kg food, how much is the emissions for methane or CO2 or N2O? So if 1 kg is exported, we can calculate how much is the methane and CO2 and N2 emissions.
Yes,
I think it is not only beef. I think it is also milk, isn't it? Because you considered that as a.
You're right. No, it's not about everything. I'm not talking about beef. I'm talking about each product, each commodity. So we keep track of each commodity's contribution to methane, N2O, and CO2 emissions. And if they are exported and imported, and how much amount is exported and imported, accordingly, we actually subtract that amount if it is exported, and I added if it is imported. Make sense?
Yeah, sure.
So there is another question: how we will distinguish carbon emission from beef production and milk production?
Professor Atul, what is the process of milk production? I mean, emissions productions from milk?
Okay, so this is the work. My postdoc is expert on this. Actually, he did it quite detailed analysis, and so he is using some emissions factors for not only the milk but also the egg and other other dairy products. I would not say only milk. It includes all the dairy products, including cheese. The cheese, egg, and milk. Actually, these are the three, and there may be some other product too. So the total dairy product emissions actually we calculate, not only from the milk actually.
Okay, thanks.
Yeah, Ravi,
go.
Yeah. So this question by Jitin, like how we will distinguish carbon emission from beef production and milk production?
Because they have a different, emissions intensity. You have to think of that way. Okay, let me explain the way. Let me explain. So in order to produce milk, how much is the biomass feed is used, right? That part become part of the carbon, right? Similarly, how much are the cows produce methane? That part become of milk product, right? So if the more feed is being used, as I have shown in my emissions, that circle figure, that more activities and more, the products have been used to produce animal-based food, So that's why the emissions goes higher. Depending on which animal is producing what product, right, and how much are their consumption of feed would determine the emissions. Enteric fermentation is independent of that, or because it is being actually produced in the guts of animals due to some bacterial activities, and we account for those emissions based on the emissions factor, for each, depending on depending on the age of, I believe, the age of actually the beef cow and monogastric animals. Make sense?
And the last question is by Eleni. How do we validate numbers reported by the model?
So as I have mentioned that we have done quite detailed validation in terms of methane, in terms of the carbon, in terms of the N2 emissions, right? And that's what we did actually. We did this at a site level, we did at a country scale, and that's how we validated our model results, right? And then we upscale it to the region and then to the global scale. Our numbers are quite different than the IPCC. If you may recall now that the total emissions from the agriculture or animal-based food is only about 11 to 12% based on the IPCC fifth assessment report. Ours is a 2/3 about of the total emissions, right? So about 30%. So it's quite a lot more than the IPCC and FOO results.
Sir, I have a small question if Ravide allows me. So nowadays we talk about these edible insects as a future food option. And also these insects are also proposed as feeds for chicken production and all, not only as food, but also as feed. So do you have any opinion on that?
Can you repeat your question?
Yeah, so I'm saying that nowadays there is an increasing interest in edible insects in some places, actually, mostly in Europe, not only as food, but also as feed also for this chicken and other meat production. So what is your comment on that, like using insects as feed and food? Yeah,
I have no comment because I'm not aware about this issue and how much will be the contributing of all these insects, to the greenhouse gas. There are certain insects which produce methane, I believe. Again, same because of they're actually in their they have some anaerobic conditions in their stomach that actually produce some little amount of methane. But I'm not aware about any contribution from the insect to the CO2 and other greenhouse gases. So I would not say that I'm expert on this. So I would not able to give you the right answer to your questions.
Okay, thank you.
Okay, thank you, Atul sir, for presenting this big data analysis from Pravison. Let us thank Professor Atul Jain for a nice and interesting talk. And I will hand over it to Dr. Vinay. Please go.
Thank you so much. Thank you very much.
Thank you, Atul.
Thank you, Prabhi.
Enjoy the AGU, rest of it.
Yes, I'll go to sleep now.
Thank you.
It's too late. Thank you for staying up so late.
Thank you.
Interesting talk.
Thank you for a nice talk.
Yeah.
Thank you, Atul sir. It was a very nice talk.
Thank you.
Thank you very much.
Can you please share that paper Zhu et al. 2021?
Oh, okay. So you don't have a copy? You can download from my website.
Fine. Okay. It is right.
Okay.
Right.
You go to my website and there look for research papers, and then I just actually uploaded that paper because it is available from all other places. Yeah. So earlier I was not actually sharing, but I have noticed that others are doing it. So I can do that.
Sure.
Okay, thank you, Professor Atul. Thank you, Ravi, for chairing the session. Now the chairman is changed to Yogesh. Yogesh, please take over from here.
Yeah. Okay. So good afternoon. Now the next talk is from Dr. Mehul Pandya. So still we have 4 minutes. Should we start? Should we go for discussion a little bit more?
I think wait. Wait. I think better to wait.
Yeah, so if anyone has any discussion point or anything, they can raise it.
Just take rest yourself.
Yeah, Pramit is asking a brief water break, so you can go for a water break.
Yeah,
Maybe we can reassemble 2:15. We can stay online, but start 12:15.
Yes,
I'm sorry.
yes,
Yes.
By the time Dr. Mehul can set up his slide.
Yes, please share the slide so that first page should be visible.
Can you see my screen?
Not yet.
Can you see now, Yogesh?
Not yet, not yet.
Is it?
Yeah, I can see.
Okay, yeah. Fine. So I'll also take a break for 2 minutes and come back.
Yes,
huh?
yes, okay. Yes, please. Yeah. Okay, now shall we start, Dr. Mehul?
Yeah, I'm ready.
Yeah, okay. So, can you put it on your slideshow mode? Yeah, now fine, perfect. Okay, so welcome all. Now the next talk is by Dr. Mehul Pandya. I will give a brief introduction of Dr. Mehul. Dr. Mehul is a senior scientist and head AED at Earth and Planetary Sciences Area, SAC ISRO. Dr. Mehul Pandya is PhD in physics. He has contributed in various R&D activities related to satellite remote sensing of biosphere and atmosphere through development of algorithms for retrieving various geophysical parameters. He has been one of the main team members of definition of sensors of many ISRO satellite missions. He was one of the member of Mars orbiter mission science team. So mom was very super hit in India. So he was one of the member. This is proud for us, for all of us. His research interests include optical polarimetry, remote sensing for aerosols on Earth and Mars, greenhouse gas detection with hyperspectral observation and theoretical modeling. He has many awards and recognition on his name. Just I am listing a few. Dr. Mehul was a visiting scientist at NASA Goddard Space Flight Center, USA in 18. He is a lead author of IPCC report. He is a recipient of ISRO Young Scientist Merit Award and RSPR Pishati Award. He has around 70 publications to his credit. So I welcome Dr. Mehul Pandya to please give his lecture. Thank you.
Yeah, thank you, Dr. Yogesh, for your nice introduction. So good afternoon to all the steering committee members, Dr. Patra, Dr. Valsala, Dr. Tiwari, and other colleagues, and especially all the participants. So we have been actually very fortunate to listen to various presentations, detailed presentation on inventories, assessments, modeling, and in situ measurements throughout 1.5 days now. So today I would be trying to discuss with you monitoring of greenhouse gases through satellite remote sensing observations and radiative transfer modeling. That means I would be taking you to a vantage point from distance from the surface. So as I mentioned, there are three major dimensions involved in inventory and monitoring of these gases, either through ground measurements or some of the mathematical modeling, and obviously remote sensing observations, and not necessarily exactly satellite observation, but remote sensing observation. So our today's discussion would be around satellite observation of these gases. So as we all know that satellite observations, they provide a special vantage point from space, which we will have we can have a watch from space, and it can provide us systematic and synoptic global observations, either through polar orbits or from the geostationary orbits, which I have tried to show on right hand side of my slides, either through very low orbiting polar or from 36,000 kilometers geostationary orbits. And obviously instruments, scientific instrument on board these satellites can observe, can detect greenhouse gases and pollutant gases from various kind of optical and electronics arrangements in instrument. And it can provide us eye in the sky, which can capture state of the atmosphere and some of the exceptional phenomena which are being actually observed from air pollution point of view, greenhouse gas point of view. So just before starting of my presentation, all of us, we know, but why these space-based observations are required? Because it can help us understanding and narrowing down some of the uncertainties in terms of when we compare models versus some of the inversions, or if we want to understand point sources or things, anthropogenic or natural sources. And satellite can provide us, that tool for a large synoptic and systematic coverage. What satellites provide? Satellites can map this concentration of gases, and they are very much useful in many of the determination, calculation of emissions, and also it can provide a means of validation of some of the emission estimates. So what I would like to try to show you today through my slides and to participants, how this specific scientific instrument onboard satellite, they provide, some of the satellite-based radiances and how those radiances are converted into meaningful numbers by means of some modeling, and how those can be converted into some of gas concentration, and ultimately it can be useful for understanding various processes. So my idea is to show some of the examples and case studies which will give us unique advantages for satellite observations as far as gases are concerned. In simple terms, I will try to dwell some time for the benefit of participants, the simple physics behind these remote sensing of atmospheric gases and some of the RT modeling which go into these retrievals. And lastly, what are the future remote sensing missions for gas detection and monitoring? So total lecture within half an hour or so, 35 minutes or so, 30 minutes, I will be trying to cover these three major areas. So let us try to just understand the components which are there in remote sensing of greenhouse gases, because we define based upon scientific requirements the scientific instrument sensor, and that particular instrument would be integrated in a satellite which will be launched through a vehicle, rocket, a launch vehicle, and once it goes in the space, it would provide us various kind of remote sensing observation, and those observation data sets are generally captured at data reception site. Those data sets are then converted into meaningful data products through image processing and modeling. Those are converted into real fields of our interest, and those go into the various kind of applications. And these applications are generally should be in the for the benefit of the society. So many missions we know, satellite-based missions, these are not a full list, but important satellite missions for various gas monitoring for air quality modeling. Various missions have been there in space which provide a unique capability of observing these species from the space. I'm not going into detail, but for the benefit of students and researchers, we must understand what kind of instruments they carry with them. So what I would like to just show you various kind of satellite platforms, starting from NASA's MODIS, Terra Aqua to Envisat to Aura to Sentinel-5P. But what most importantly we need to understand it, what kind of instruments they carry, what kind of spectral range they work, because they generally work in ultraviolet, visible, shortwave infrared or thermal infrared, what kind of species it actually they can observe, and what kind of technique and instruments they have got with them on board. These are very important for students, for researchers to understand various kind of spectrometers and FTIRs they carry on board. So I'm not going into detail. We may dwell some time on some of real understanding of the basic principles behind this, because remote sensing of atmospheric gases can be, as I said, can be done from ultraviolet to optical to thermal to millimeter wave and microwave. This ultraviolet optical, we know that based upon solar reflection or thermal emission or microwave emission, one has to understand the signal from the surface as well as from the pollutant or for atmospheric gases. The physics behind those, physical bases are quite interesting, but people generally use hyperfine spectroscopy and gas correlation techniques and various kind of instruments. They work in various spectral bands, and many species of our interest can be understood, can be retrieved from this kind of thing. So what is the takeaway from this slide is to the satellite remote sensing, which we generally get products, we consider it is take it for granted, but state of the art technology. They go into defining, developing those, and then retrieving from various kind of signals, either from various frequencies or wavelengths, ultraviolet to micro frequencies. So it involves a lot of physics. So as I said, visible to shortwave infrared satellite sensors, they receive based upon the reflected energy. That means this is a passive kind of reflective remote sensing, where you are actually observing the reflected radiation from surface as well as from the atmosphere. Other thermal infrared frequencies or wavelengths, they are actually capturing the emission and thermal emission from the surface as well as the atmosphere, and some of active kind of micro or lidar kind of thing, which will have their own source with them, and they illuminate the surface or atmosphere and try to get the echo out of that and try to find out the species. What basic physics go into this? It's very interesting figure. The sun is the source of the energy, and that electromagnetic radiation that it emits, it passes through the atmosphere and tries to reach at the surface depending upon the wavelength in which it is working. In the atmosphere, it will be actually interacting, radiation will be interacting with the molecules and aerosols, and that will be scattered or emitted from those species, and this reflected radiation from these species are then captured at the sensor. So that solar radiation interacting with the molecules and aerosols, it actually is captured by sensor, and sensor which is working in various kind of wavelength ranges here, ultraviolet to visible to near infrared wavelength region, it captures those signals, and signals which are as a function of wavelength, once they are plotted, they have specific absorption signal for each of various kind of atmospheric species, and depending upon this specific spectral signature and specific behavior based upon the spectroscopic behavior of that particular molecule, it actually modulates the frequency, and which are recorded on board sensor. So these kind of, we know from the sun, you have a incoming solar irradiance at the top of atmosphere, but when it gets reflected back, many of the energy bands or many of the wavelengths are eaten away because of various species. What kind of species they actually come into the picture? Either it is invisible to shortwave infrared or from thermal infrared. So from CO2 and CH4 and H2O, which are the main players, and oxygen in the visible and those things. And for thermal infrared, there are many species which actually come into the picture. These kind of spectral signatures are used for understanding the spectroscopy. I have tried to put a simple slide for the benefit of participants, how satellite generally does the basic retrieval of trace gases. This I have taken an example of TROPOMI, which has got TROPOMI tropospheric monitoring instrument of ESA. It's an imaging spectrometer which covers approximately 27,000 kilometer swath, approximately 5 to 7 kilometer spatial resolution, and it measures light from ultraviolet to shortwave infrared region with very, very high spectral resolution of less than 1 nanometer, which is must for understanding greenhouse gases. What it does, this satellite, it carries this tropomi instrument. So once this tropomi instrument, it tries to capture the data set through the column of, let us say, gases. Once that radiation passes through gases and it is observed through certain optics, and you get, because it's a dispersive element, you get a line spectrum out of it. These line spectrum represents the signature of this gas. And what kind of line spectrum it would give? It would give a line spectrum of this nature, where it would eat away some of the wavelength range, wavelength positions, or let us say energy. And these, you know, absorption feature, they are actually characteristics of specific gas. So this is the physics behind the spectroscopy of any of this specific gas, which actually is then used. You know, once we understand the specific signature of gas, let us say we have understood that some of the CO2 absorption is occurring at this particular location, then the radiative transfer modeling comes into the picture, and as a function of varying CO2 gases, we try to model. Here we have tried to model for CO2 as a function of varying CO2, and these absorption features would be systematically can be computed, and by understanding these band gap, band depth, one can invert the specific gas. So this is the basics of trace gas retrieval. After just understanding this basic, how unique are observation from space, you know, so we'll try to see, because we know it can cover larger area, it can be used in process-based model and capture some of the state of atmosphere and major events. So we'll try to one by one see. Let us try to see synoptic view. You have seen, most of you have seen this kind of images, synoptic views over India of various pollutant and greenhouse gases, which are now available through many of the satellite-based instruments, which can be, it's not that easy, but once you have handle on that, one can use it for various purposes. So it can provide us a synoptic view over India. And once you have this kind of observation, it can be used with some modeling and assimilation scheme. One can understand, because the use of satellite data, because of its great synaptic, systematic and routine coverage over globe, gives us a handle to use it in modeling. Or I will show some of beautiful events to capture those events through satellite data sets for various kind of species. I will quickly go through these various kind of examples where we would be seeing like nitrogen dioxide to carbon dioxide to sulfur dioxide, ammonia and carbon monoxide, how they are being captured over various events. So as we have been discussing, and people know it very well, because of COVID pandemic, there was a significant lockdown across the world. And in India, there were 4 major lockdown durations were announced, so starting from 25th of March to May 31st, and lockdown was opened on June 1st. And because of all the traffic activities, commercial activities, industrial activities were seized, these actually led to less pumping of these gases and particulate matter. And that's why it gave us a beautiful advantage of understanding some of the baseline or less pollutant data sets as far as satellite data sets are concerned. So I'll try to show some of our work where you have seen, many of you have seen this kind of observation, but the power of satellite, because compared to normal year, lockdown year, how it actually changed the scenario. And these are the images of nitrogen dioxide, which actually you can see through various months how they get decreased in the month of March, April compared to March, April of 2019. So I'm just try to now again give you a beautiful example, which we have tried to convert these into 3D map, where if you see April 2019, we consider as a normal year, where you could see some of the cones of over various cities and many of the populated areas of Indo-Gangetic Plain or metro cities of New Delhi, Kolkata, Chennai, Hyderabad, Bangalore, Mumbai or Ahmedabad. But there are other significant cones which actually are related to power plants. So what happens once, what is the power of satellite that actually gives us a beautiful narration of the effect of reduction of NO2 emission during lockdown, where all the buzzing traffic and other activities of various cities and various populated areas of India, they actually got shut down. And most of the power plants, they were working, and you could see almost similar kind of pattern and numbers over those power plants. So is a beautiful example of satellite remote sensing. And if you could see over a period of March to May, for normal year, the NO2 over India was quite high compared to this particular time frame, where you could see exactly matching with the lockdown days. Those numbers get reduced when lockdown was about to open. People try to rush through for various kind of shopping and those kind of thing in some of those open hours. That activities, they are captured, again it gets reduced, again it tries to match these. So these kind of lockdown effects can be observed through satellite. And city level, obviously we could observe some of those numbers which actually reduced by the 50 to 70% over various cities of Nagpur, Ghaziabad, Greater Noida, and many of various metro cities of India, where Mumbai or Delhi, buzzing cities, they show very less pollution during those days. Another example for carbon dioxide, how satellite observation, I'm just trying to show you some simple but still effective examples to just there are many examples, many studies, but out of those studies, some interesting examples I would try to show you. The carbon dioxide concentration using OCO and other satellites, they could be used to understand the anthropogenic contribution. So for US or China, the columnar concentration anomaly over US or China were in the order of 2 to 3 ppm, which were captured through subtraction of those days concentration from the average behavior of the region over a period of time. So this could be considered to be a very good tool for understanding many of these kind of anthropogenic contribution in terms of atmospheric carbon dioxide. ISRO also had tried for hyperspectral experimental mission in polar orbiting satellite, which works from 400 to 2500 nanometer with 30 nanometer spectral and spatial resolution with 30 kilometer swath, and which has got approximately approximately 316 spectral bands in these particular region, and which we have also tried. This experimental satellite, which we could try, we were successful in deriving some of these carbon dioxide columnar concentration. This is an example of Dayapar, Kutch in western part of Gujarat, western part of India, where there was a plume of carbon dioxide could be captured through HISIS, that spaceborne ISRO's mission, and those actually correspond to the thermal power station of that particular region, which is a Kutch thermal power station. So these were used for various kind of experimental, spectroscopy and derivation of CO2. The other example could be the SO2 emission from satellite platform. So, this from the NAT example, where sulfur dioxide, how it has, because of various activities over India, how it has increased in a period of 10 to 11 years, and how hotspots have come up in various parts of India. During lockdown also, most of the regions, this was a normal case, and this was the lockdown case where, sulfur dioxide got decreased, except in this particular place where it showed a increasing trend. Obviously, this kind of volcanoes, once they push some of these kind of gases in the atmosphere, those are actually can be captured through satellite data sets, which we tried to do over last year at Krakatau, Indonesia, where you could see the plume of SO2 could be captured through some of these satellite data sets. So other than anthropogenic activities, some of these natural activities can also be captured through satellite-based observation. The species, which is very important, ammonia. Now I'll try to show one or two examples for that, which actually show the activity related to agriculture or industry, and they are the main culprit of releasing ammonia. A beautiful picture from a paper by Dam in Nature, which showed great amount of hotspots over part of various parts of globe, where India was one of them. And this was done using ISI infrared atmospheric sounder interferometer measurements for various dates and time. And total study found out approximately 250 hotspots with various diameters smaller than, let us say, 50 kilometers. And it was also categorized that all those hotspots, I'm not expert in that, but what they could show that all but 7 those hotspots were linked to anthropogenic activities, and 83 hotspots were found to be from intensive animal farming, 158 from the industrial region, 130 sites were with the fertilizer-based factories. 6 hotspots could not be linked to definitive source. So what I would like to just tell you, try to brief you that this kind of interesting science can be brought out from this. And the last species which I would like to show you for carbon monoxide, which actually has a link to great climate change variable, and because of incomplete combustion of fuels through some of coal mines, some of the forest fire, and those activities, carbon monoxide can be captured. So obviously these kind of stuffs are available over net, but what for students and for researcher, it's very interesting to note down that these kind of observations are quite useful because many of those forest fire in Indonesia and eastern region actually hampering many parts of northeast, which could not be captured through some of the modeling activities, but through satellite observation one can easily find out what kind of sources they are working towards pumping this harmful gas into the atmosphere. So the last part and very interesting part, I will try to show some of the latest and good greenhouse gas retrieval related activities at Space Application Center, Ahmedabad. What we have been doing. People know is Avery's NG. Avery's NG is a hyperspectral spectrometer, airborne spectrometer of NASA, JPL, and ISRO NASA. We had a great run and great, 2 campaigns of phase 1 and phase 2A in last 5 years or so, where we captured somewhere around 70 sites across India. And these are unique data sets we have gathered from airborne heights from 3 kilometer to 5 kilometer flying height by our ISRO's plane. And what does it give? An average NG measures radiance is in 432 spectral channels through 350 to 2510 nanometer, and it has got, though CO2 and CH4 have their requirement of retrieving CO2 and CH4 is quite challenging, but we try to do through various kind of mathematical modeling and other tricks, where you could see, as far as carbon dioxide is concerned, a beautiful feature of carbon dioxide is residing in this region, and very minute for methane. But these kind of retrieval are quite challenging when it is in the background of water vapor absorption, which is present throughout almost the spectral window. So what we have done is, I'll just try to show 1 or 2 interesting example how methane gas or detection, plume detection was done. If this is an image of Ahmedabad region, it's a false color composite of Ahmedabad region. This is a Sabarmati river. This is old Ahmedabad. This is new Ahmedabad, and there is a barrage here, Vasana barrage. And this particular image, you could see it's a completely clean and very beautiful image. I'm showing it in very close, small portion of that. But we had a lot of ground observation we captured during that particular flight in synchronous with the flight time. And with the help of radiative transfer modeling, what we could do through RT modeling in these particular average NG bands for varying concentration of methane, we have tried to compute those transmittance as a function of wavelength. So as you could see, as methane concentration increases, this particular absorption features they gets enlarged. We had line by line calculation of methane absorption, which is totally engulfed in water vapor signal. So there are tricks, mathematical tricks to decouple water vapor effect from these methane effect. And we convolved these signals with respect to spectral resolution of average NG spectral bands. And this is the realistic picture, realistic mathematical signal which one would expect from average NG clean images. So we have used these channels and try to do, many of these mathematical modeling based upon absorption spectroscopy, which measure the absorption as a function of wavelength region, and this cluster tuned matched filter technique was used to understand the methane plume detection. What actually this MF does it assumes that gas plumes are modeled as a linear superposition of gas signal and background clutter, and there are detailed mathematical modeling goes into this particular exercise, which decouples the effect of background clutter and gives us beautiful results. So this, as I showed you earlier also, I have shown you this particular image. Now I'll just click and try to show the detection of methane plumes from this particular data set. So the data, which is looking like very beautiful and clean image, which can't be, one cannot expect any of perturbation from the atmospheric. So based upon RT modeling and some of the mathematical modeling, one could derive this methane plume, which is, if you see closely, there are two plumes, one here. I have not tried to smooth it out. One can smooth it out, these particular images. These are original outputs. So two plumes which are coming up from nowhere. So when we see this particular thing, it is basically from landfill, solid, dump site of Pirana dumping site of Ahmedabad, where we have all the garbage and solid waste is being dumped. And once we superimpose the methane plume, it actually is coming out of this Pirana dump site. And this plume actually had a length of approximately 5 kilometers, where Kankaria Lake is situated. It travels up to that particular. We ran WRF and other models and try to see the fields of various wind patterns and those things. Those all they match. And small peak was also seen. So what was these again same image? I have tried to put it in red color, where one side it is a solid waste landfill site, and other side which is a small torch kind of source. It is nothing but sewage treatment plant over Pirana. So these airborne hyperspectral data sets combined with the RT modeling can be used for point source detection, which people try to use it for various applications. We also tried it over part of quota for carbon dioxide concentration retrieval, where over super thermal power station of Kota, Rajasthan, we had a flight at 4.1 kilometers altitude, and based upon that particular calculations, we computed the sensitivity of CO2 in various spectral regions, and we could confirm that if carbon dioxide varies around 35 to 40, 25 to 30 ppm, it has got a sensitivity. Every NG has a sensitivity, and CO2 could be captured. And if we put a transect over that, CO2 was showing starting from 470 to 560 ppm. So this kind of activities can be done. For CO2 estimation from over Ahmedabad also we tried, and we had got lot of in situ measurements synchronous with the average NG flight in situ observations, where we could see from airborne flights, these spots were showing high concentration on ground also. They are matching. I would not say it is exactly matching, but high and low correlation with in situ measurements were also observed. So just now coming to last two slides, this is an old slide, but I like this slide from Nature Tollefson paper, where we know various kind of satellites have been there put into space, but in future we have got exciting future after various kind of GoSat, OCO and other satellites, Microcarb and Merlin will be there in space. And the Merlin, which is nothing but a methane remote sensing LIDAR mission, I am just excited to understand its basis and its retrieval techniques. So it actually is DLR seen as active LiDAR system, which will be working for working in 2 wavelength regions somewhere around 1.6 micrometer. And that particular 2 frequency integrated path differential absorption, IPDA kind of LiDAR instrument will be used, which is from DLR, which will be used for understanding the methane. So I'm not going into many other details, but some of the updation and some of the future plans which people are thinking all over the world. 2 examples I would certainly like to show you. GHG set is being actually considered where it would be trying to pinpoint the point sources of carbon dioxide and methane with the measurement precision of less than 1%, with the spatial resolution less than 50 meter per pixel. That means it can give us a very beautiful detailed pictures and can pinpoint target the GHG emitters, and it can provide a very good inventory tool. The other things which are coming up is low altitude, UAV based missions, UAV based instruments, and very COTS kind of instruments are available, and which can be mounted on drone. And once you have that drone working in some height, at least a few meters height, it can illuminate the gas plume. And likewise, the flight path was like this, and the retrieved map over that particular methane gas concentration was easily computed. So these kind of techniques are also and tools are coming up. The last section and last slide, which is very interesting, and probably I would like to just brief the participants as well as committee members also that so our view that India's greenhouse gas sensor, which should be there in space, working in visible to shortwave infrared range with the spatial resolution of 5 kilometer at 14 kilometer spatial coverage. It should have nadir and limb viewing capability, and we should be able to design first airborne model and then should try for spaceborne, and it would actually target 4 of the species, and with the challenge is very, very high spectral resolution of less than 1 nanometer with very great signal to noise ratio. So challenge lies in that. The importance of this, anyway, we all know the spectral windows which it would sample, but the requirement from the scientific community, the maturity of scientific community across India is much more souted. And we will be also discussing some of these things in panel discussion also, if time permits. Why those things? Some of our calculations earlier, some 7-8 years back, it shows that if you have spectral resolution of around 1 nanometer, let us say 0.5 nanometer, it would have a transmittivity and some of the sampling like this. As spectral resolution increases, obviously the strength of their capturing the features, they increase, and sensitivity is quite high, where spectral resolution is quite high, and after a certain point of time it gets saturated. So we require very, very high spectral resolution for India's greenhouse gas emission, and which would be able to give us to put some of the gap areas of Indian space program. This is only missing link in this greenhouse gas measurement. So And yeah, last slide, which I have got from my colleague, Dr. Imran Giraj, that for students, we know a lot of satellite data are available. This is from OCO2, India average ppm, which one can understand over a period of time as a seasons, which has got a beautiful trend, as we generally see similar trend at Mauna Loa. Once we understand this kind of patterns, what Imran has done, that apply the artificial intelligence techniques for predicting the same through various kind of algorithms, and this kind of challenges for various species are also available. So this is my last slide, and we know that satellite-based instrument can provide greenhouse gas watch from space, which will be very much useful for understanding the state of the atmosphere, which is also useful in modeling. It can give us concentration and identify sources and sink. And it is also can be useful for validation with respect to ground as well as vice versa. And GHG observation with a quite maturity has started in 90s, and now steadily it is increasing, and will have a very great scope of continuing and to expand in future with the availability of new sensor and techniques. And obviously many opportunity exists for students and researchers in this field, who are working from mathematics, physics, and various kind of computer science and other science and engineering background. So with this, I stop, and I thank IITM Pune and all the colleagues, Dr. Valsala, Tiwari ji, Dr. Prabir Patra, and all the scientific steering committee. And I would mention some of my research scholar work, Akhil and Tejas here, Imran, and obviously I thank Director Sek for giving us this opportunity. Thank you very much.
Yeah, thank you, Dr. Mehul, for giving such a nice overview about the satellite remote sensing of the global programs, as well as it is really excited to know that India also planning GHG sensor remote sensing. So this is really fantastic. So I'll go to the questions. So first question is from Vinu, and he is asking a similar question. Is ISRO planning onboard instrument for GHG in the future? I guess you have replied. Is SAC participating in the retrieve?
Yeah, just Dr. Vinu and the other members also. ISRO has geared up for this kind of thing, but now the scenario has changed. It's not only scientists within ISRO who would be going and asking for some of these requirements. The idea is now, reversed. Now demand-based and scientific requirements from various user groups, various scientific group, various researchers group must come at the highest level. And these are the forums, I think, which will help us in last one of the last meetings also, or workshops also. I said same thing. We need to put a white paper or having a various kind based upon various kind of discussion and resolution should be there. And subsequent to that, we should be working over finalizing some of those scientific requirements with the help of obviously from ISRO's scientists, ISRO's engineers, and then it should go, because it's very, very important to have our own satellite. As I showed, one of the satellites which is there in space, which is not in now our domain, which is a special satellite, but ISRO has already shown some of those capabilities in space. But as far as this kind of greenhouse gas or pollutant gas monitoring is concerned, the requirement is quite stringent. If we start from today, we may have some years, couple of years to put it in space. So we should, I request again to participants and to all the colleagues who are here, we can have a detailed discussion and we can come up with some of those requirements.
Yes, we'll include in panel discussion. Yeah. Okay, so the next question is SAC participating in the retrieval of any GHG from existing satellite spectral data?
Yeah, obviously. We have got 2 satellites in geostationary orbit, INSAT-3D, INSAT-3DR, our own satellite, where ozone and some of other gases are being retrieved, greenhouse gases are being retrieved, and from MOSNEC sites, those data sets are available. They have got sounder, thermal infrared sounder, 19 channel sounders are there, geostationary satellites, and so some of those data sets are being actually used, and physics-based algorithm with the collaboration with Wisconsin University, we could do that. And independent of those, we are also trying to do on our own using OCO, GOSAT kind of data sets, trying and test TES and IASI. We do based upon case studies, we do our own retrieval, because if we will be having a satellite in space in future, scientists and engineers working at SAC will put that particular, but how to retrieve the mathematical modeling, RT modeling, which is one of the challenging areas, and professors and scientists, they don't try to give their time in those activities. They are interested more in only products and science out of it. But the most challenging work and most difficult work is to generate the digital number to radians to the meaningful number, the retrieval algorithm in that. So in that also, lot of activities we are trying to do on our own. But if anybody is interested, capable of doing that, we'll be very happy to have them in our team. IIT, Ravi Kunchela and other our colleagues, they have been in touch for some of the applications with the help of Dr. Patraji also for chemical modeling and transport modeling and all those things. But the gap from satellite-based engineering units to the greenhouse gas concentration, that is a challenge lies there. It's a beautiful subject for any physicist, mathematician or modeler to go into that.
And next 2 questions are common from 2 of our participants, Gayatri and Ellen. They are asking that satellite measures column integrated values. So when we compare it with the observations, basically what are the challenges we face? So how accurate is remote sensing data should be there so that it can be comparable? There are many studies, but maybe they are asking as a participant.
I think participants are quite aware and quite mature, so that's why they are asking a very pertinent and difficult question. It's a yaksha prashna. It's a very difficult question. So as we all know that columnar concentration versus the various profiles of any species. So satellite has got their own. Let me just give 1 minute how satellite works. Satellite works in specific spectral channel. Spectral channel would be either very sensitive to some of gases or non-sensitive to some of gases. Let us say 1.6 micron for methane. So if you put a channel in that particular thing and just beyond that another channel. So first the absorbing channels weighting function is quite up. That means it gets data sets, gets observation, it gets absorbed in that particular layer of that species where it is lying. The channel which is open or transparent to that, it will capture this surface layer observation also with that. So now based upon differential absorption characteristics between these 2 channels, people try to understand the columnar concentration and retrieval of that. So obviously for most of the species which are very nearer to their sources with a good residential time frame and which has got very not that great dynamic in nature will have very good match, or at least good match, not exactly 1-to-1, but for gradient it will pick. But for some of the species you may not have any kind of that good correlation. So one has to understand the technology and the limitation of those versus surface thing, because if I want to capture the surface level observation, then I will be having a challenge from the clutter and background surface reflection, so which makes very difficult situation for any retrieval once if one wants to understand of very near surface. So there are certain challenges, but obviously with the help of, I think, active sensing like LIDAR and some of those sensors, probably we may have a better picture. So it's a difficult question to answer, but probably I try to put both the aspects.
Yeah. So one quick question from Chaitanya. So is there any drone measurement, GHG measurement using drones? Any instrument developed or any idea about that?
Yeah. I showed there are certain off-the-shelf instruments are available. I showed I can pass on those details to interested. Those instruments which can be put on the drone, people have used it, but they are not of great quality, not great scientific quality as I understand. So for that, research labs, they have to dwell time, do research and put lot of money and effort about it. But for some of COTS and some of off-the-shelf instruments are available, people use it. What they do, they measure at the ground various spots, and they measure from the drone also, and they try to correlate and try to make some of empirical based retrievals. So it's not that great scientific retrievals as I understand, but there are instruments available. I have some details available, those papers and those I can pass.
Okay, so next is Shamil is asking from Japan. Do you have co-located observation with Tropomi?
Co-located on ground, I understand.
Right. I mean, any observations from ISRO side, from SAC side, which is co-located with the Tropomi?
We have a lot of co-located observation of various gases and particulate matter in last couple of years, and our students who are also part of this workshop, they have been working day and night. We have got diurnal measurement of some of gas species and particulate matter on the surface, and we try to do with some of the government's CPCB's stations also. 2 SUFFER stations are also located at SAC, Space Application Center. So we have got some of the co-located data sets. We have tried to use it for various kind of comparison also. So yes, Shamil, Shamil, we have some of those data sets.
Yeah, Shamil is just adding in his question. Actually, it's not question. He's giving some comment. Yesterday, there was a report about measurement with Bruker 125 mobile in India. Technically, 125 mobile doesn't qualify for inclusion to TCON dataset, but I would encourage the retrieval and comparison with satellite products. Even Bruker EM27 is now giving promising results. So this is just comment.
I think from NRSC, Mahesh's work, I think, from Hyderabad. Yeah, so right, the point taken. So, thank you.
Right.
Thank you, Shamil.
So from IASC, Professor Prasenjit Ghosh is asking, according to you, what is the sensitivity of detecting GHG signal with minimum uncertainty using satellite-based observation from Indian region? We understand the variable interference from water molecules at seasonal time scale.
Yeah, very nice question, Professor. As I understand, what general numbers are somewhere around as far as carbon dioxide is concerned, columnar concentration, various literature, they show 1.5 ppm V on some of easy terrain. But as far as India is concerned, we have seen some more uncertainties somewhere around 2 ppm V. So we have got certain data set, certain analysis which suggest, and he is quite right, as far as some of the tropical regions and engulfing in water molecules and some of other issues, it decreases some of the uncertainties, it increases those uncertainties which generally are not reported in literature also. But we find somewhere around 2 ppmv uncertainty in CO2 over many of the sites or some of the sites over India.
Dr. Prabir asking, I'm curious, what is the design plan for nadir and limb viewing sensor? Shamil and I did some OSSE for CO2 limb sensor, but it was not very encouraging. So for sourcing of inversions, so GOSAT was designed for nadir only measurement.
Yeah, you are right. Dr. Patra, you are absolutely right. The experiment which we have done in 2 missions, one was in limb viewing, specifically only limb viewing sensor, which we called YouthSat, we are having hyperspectral observation of the limb mode, and HISIS, which was completely for nadir view. But there are certain designs with the high field of view and limited limb view capability. Some design aspects are being deliberated, are being discussed. As far as nadir view is concerned, it's easy to do that. We have been able to do it quite easily, but you are absolutely right. This is our scientific requirements, but to convert it into engineering, reality, it is going to be quite challenging. But there are some plans which we have been discussing internally at ISRO, Space Application Center, where we may have with the high field of view and some of those kind of specialized kind of sensors which work on time domain integration kind of principles. We may be having that kind of capability, but still all those things are in discussion phase only.
Yeah. So there.
What Patra is saying is they have already. I'm not aware if they could share some of their experience, or we could have some discussion for understanding their experience. I would be very happy, Dr. Patra and Dr. Shamil, to have those discussion from your wisdom. Our space program and our community may get benefit also. So I would be interested in learning some of those things also.
Yeah. Dr. Patra gave one paper, Patra et al. JGR 2003. There they have, I think, they have done this OSSE experiment for CO2 limb sensors.
Okay. It is checkbox. Huh?
Okay, I think let's come back to this in the panel discussion. I think Mehul is in the panel, right?
We'll do that in the panel.
Mehul is in the panel.
We'll do that.
Because it will be a long discussion. So
this is very important. Okay, so we have a few questions, but I would advise to just close this, and then those who wanted to ask really talk to Dr. Mehul directly by email. So if any questions or any comment you have. So let us thank Dr. Mehul Pandya for giving such a nice lecture, and then which is really benefited to all of us and young scientists who really learn a lot about the remote sensing and then GHG observations through various satellites. Thank you, Dr. Mehul.
Thank you, my pleasure. Thank you.
Vinu, over to you.
Thank you, Yogesh, for chairing this session, and we'll now break for lunch. Now we'll come back to 2:30 post-lunch session, and I will chair that session because Yogesh himself is presenting there. Okay, so everyone come back up at 2:30. Thank you very much.
Thank you.
A very good morning to all of you. It's a pleasure to invite you all for the inaugural of third greenhouse gas workshop conducted this year at the IITM. So the official title of the workshop is National Training Workshop on Greenhouse Gases, Observations and Indoor Modeling on Regional Perspective. So today we have the Director IITM to give a welcome to the audience and welcome to the Okay.
Yes, Vinu.
Okay, Yogesh.
Yeah.
We'll wait another 1 minute.
Okay. Can you see my slide?
Yeah, we can see. Can you move it? Go forward.
Just a second.
Yeah, okay. Fine. Okay, shall we start, Yogesh?
Yes, I'm ready.
Okay. So very good afternoon to all of you. We are post-lunch session starting. So we have our next speaker is Dr. Yogesh Tiwari. So he is he is working at IITM. He did his PhD in greenhouse gas measurements and modeling from Germany, and then he moved to IITM in late 2000, and then he started up setting up the observation site in Sinagat, and that is one of the long-term observation of CO2 from an Indian station as well as methane, and it has collected so far more than 11 or 12 years of observations of CO2 and another 7-8 years of observation of methane. So today he's going to talk about different techniques and platforms used for GHG monitoring in India. So we welcome you, Yogesh, for your plenary talk.
Thank you, Vinu. So I will be giving overview of IITM GHG programs, which we have set up sometime in 2009. And later we have inducted other monitoring techniques and platforms in our journey. And many of the GHG monitoring activities in India is already covered by Chaitanya. And I am focusing here mainly IITM as well as some of the observation which is really not yet discussed here. So for the young scientists, for the young people who really entering in greenhouse gases field, and basically they want to come in this field and then understand the research. So this is very basic figure which is showing basically the greenhouse effect. So what is a greenhouse effect? So you can say that when the solar radiation in visible range comes to the Earth surface, and then the Earth re-radiates in the form of infrared radiation. So these infrared radiation are really absorbed by the greenhouse gases, that is carbon dioxide, methane, and then water vapor, and then other gaseous. And then they absorb, and then again they re-radiate towards the Earth, and then towards the so that when they re-radiate, then the temperature of the surface really starts increasing, and then in turn there are so many changes in the climate, and then you must have heard about global warming, climate change, the big words. So these gases are mainly responsible, and they require major concern because their lifetime is long. Like CO2 lifetime is almost 100-year time scale, and methane lifetime is close to 10 to 12 years time scale. So once they emitted, and then they stay in the atmosphere. So what is the basically why should we give much attention? That's why I
Yogesh, it looks like some technical problem. We lost you. We can't hear you.
Yes, somehow I think I also heard some even difficulty before.
Now also not. We are not hearing you.
Yeah.
I think I phoned him. He's fixing the issue.
Okay.
you.